you guys? I hope you're having a good weekend so far. It's probably Sunday for you if you're catching this right when I've uploaded it. So welcome back to another video. This time I have for you a science kind of fact video. I found this article on a science website. I actually subscribed for $1. I think I get about 6 weeks. So I'll try to read a few of these if you like them. This one is called 10 Mysteries That Physics Can't Answer Yet. It's broken down into like 10 articles. So the first one is, what came before the Big Bang? Has the universe existed forever, or was there something before it? To find out, we need a working theory of quantum gravity and a new conception of time. Pause, rewind. Suddenly, the outward rush of 200 billion galaxies slips into reverse. Instead of expanding at pace, the universe is now imploding like a deflating balloon, faster and faster, smaller and smaller. Everything hurtling together until the entire cosmos is squeezed into an inconceivably hot, dense pinprick. Then, the screen goes dead. According to the Big Bang Theory, our best explanation for why space is expanding, everything exploded from nothing about 13.8 billion years ago. Cosmologists have been able to wind things back to within a tiny fraction of a second of this moment, but now they're stuck. The trouble is, our understanding of space-time, and gravity in particular, is built from Einstein's equations of general relativity, whereas the extreme conditions of the very early universe can only be described by quantum mechanics. No one knows how to reconcile the two to take us further back. The rules we have simply don't work in that regime, says Carlo Contaldi at Imperial College London. Nothing makes sense anymore. That's a problem for our origin story. Did time begin with the Big Bang, or was there an epoch before it? Some insist that if we rewind the universe far enough, time just stops. But Lee Smolin of the Perimeter Institute for Theoretical Physics in Waterloo, Canada, is having none of it. It's a cute idea, but there's not much evidence for it, he says. In fact, Smolin wants to see the idea that the universe has a starting point dropped entirely. We can only hope to explain why our universe is the way it is, he says, if there was something before the Big Bang. It's about cause and effect. To arrive at satisfying explanations for why things are as they are, we draw on previous events that led to the conditions we see. One possibility is that instead of a bang, there was a bounce. In this scenario, rewinding our universe would not take us back to a point containing infinite mass in an infinitely small space. Instead, it would take us through the unimaginably hot, dense beginning of our universe, and out the other side into the unimaginably hot, dense ending of a previous universe. Acknowledging that something came before the Big Bang would open the door to explanations of how the universe came to be just right for life. Otherwise, we either have to accept that our perfectly crafted universe was just a fluke, or that it is one of an infinite number of universes, most of which look very different, and we only think of it as special because we're in it. Or perhaps our Big Bang was one of many. Some think our universe popped into existence as a bubble in a frothing sea of universes. This idea gives our universe a beginning but introduces an everlasting multiverse. Can we ever really know? Small in things we could soon see clues in the cosmic microwave background, radiation given off by the early universe. It's possible that ripples in space-time known as gravitational waves might also survive a bounce. Cantaldi is not holding his breath. We need a working theory of quantum gravity, and a new understanding of time, he says. Without that, I don't think we have the tools to even pose the question properly. So that was kind of a deep one. But the next one is a little less existential. It is, how does a bicycle stay upright? Some of these things might be a little surprising to us non-scientists. Like, I didn't know that scientists didn't know how a bike stands upright. Well, I guess we're not going to find out. So. We thought we knew the maths behind cycling. We were wrong, and our efforts to figure it out are leading to some weird and wonderful new bike designs. In 2011, an international team of bipedal enthusiasts dropped the bombshell that, despite 150 years of analysis, no one knows how a bicycle stays upright. Across the world, riders dismounted and stared at their bikes in disbelief. What they had been doing for years was a feat inexplicable by science. Well, sort of. What we don't know are the simple, necessary, or sufficient conditions for a bicycle to be self-stable. Necessary or sufficient conditions for a bicycle to be self-stable, says Andy Ruiner, an engineer at Cornell University in Ithaca, New York. We've relied on trial and error engineering to construct stable bikes that aren't prone to toppling while in motion. Explaining how they work mathematically requires around 25 variables, such as the angle of the front forks relative to the road, weight distribution, and wheel size. Before 2011, researchers had reduced this profusion to two things. One was the size of the trail, the distance between where the front wheel touches the road and where a straight line through the forks would meet the ground. The other was the gyroscopic restoring force that acts on a spinning wheel to keep it upright. Ruiner, I'm probably saying his name wrong. Ruiner and his colleagues, including Aaron Schwab of the Delft University of Technology in the Netherlands, and Jim Papadopoulos of the University of Wisconsin Stout at Menominee. I've never heard of that place. Not only revisited this mathematics, but also skewed the trail and gyroscopic forces in prototype bikes to make them technically unrideable. To everyone's surprise, the bikes were still stable. The researchers haven't been resting on their saddles since. Last year, Ruiner unveiled a bicycle, a cross between a bicycle and a tricycle, with spring-loaded stabilizing wheels that can be adjusted to vary the rider's perception of contact with the ground. By studying the influence this has on how the rider steers and remains stable, he hopes to gain new insights that might lead to more easily controllable bicycles. It's still an uphill struggle. I think the real understanding of bikes requires a mix of what we did plus some kind of brain science, says Papadopoulos. Human riders act in extremely complex yet intuitive ways to keep a bike balanced and on track. At very low speeds, for example, we recognize that the handlebars become useless for steering and instead direct the bike by wobbling our knees. Why, we don't know, says Schwab. Yet another bike-based mystery that could be around long after we've worked out the origins of the universe. Does that one surprise you? There's still some even more random ones coming than this. Here's another one that's more about the universe. This one's called, Is the Universe Infinite or Just Very Big? I've always heard that it's infinite, but it sort of never made sense to me how that was possible. Again, we're not going to find out the answer in this article. So, the size of the observable universe is easy enough to measure, but what lies beyond the cosmic horizon? We have a long way to go to find out. Just to put things into perspective, this article was written in 2015, so maybe we're not as far off of finding things out now that AI is so close to taking over. We've known the size of Earth since the time of the ancient Greeks. The Sun, solar system, and Milky Way, no problem. But when it comes to the size of the universe, we haven't got a clue. It's weird. The size of the observable universe is one of the more precisely known quantities in astronomy, but the size of the whole universe is one of the least well known, says Scott Doddleson, a cosmologist at Fermilab in Illinois. One way to think about the size of the observable universe is to consider how far light emitted at the Big Bang could have travelled by now. According to our best cosmological models, the distance is about 46 billion light years. This is the cosmic horizon, a sort of three-dimensional equivalent of the 2D horizon we see on Earth. That is as far as we can see and how big, empirically, we can observe the universe to be, says Adam Rees of Johns Hopkins University in Baltimore, Maryland, who shared the Nobel Prize in 2011 for the discovery that the universe's expansion is accelerating. Of course, we are pretty sure it goes out much farther. Why? Because the universe looks very similar no matter which way you look. Take the cosmic microwave background, or CMB, the radiation left behind by the Big Bang. It's largely uniform across the sky, and we have no reason to think that would change beyond the cosmic horizon. There are no signs the universe is tailing off, so it would be a surprise if it abruptly ended. Daniel Essenstein of the Harvard-Smithsonian Center for Astrophysics says that if the universe is only a little bit larger than what we see, we might expect to find hints of structures much larger than galaxy filaments, formations of superclusters of galaxies. These hints would show up as wild variations in the temperature map of the CMB, the cosmic microwave background. But they don't, which implies that the universe is much larger than our little observable corner. If that's the case, Essenstein says it will be a struggle to figure out how big it is. It might be 1,000,000 times larger, or 1,000,000,000,000, or even infinite. A truly infinite universe might be tough for us to comprehend. Particularly perplexing is the idea that if the universe is infinite now, then it must have always been so, even during the earliest moments in its history when the distances between objects were much smaller. But we would have to go a long way to rule it out. Okay, so number 4 is, how long does a proton live? They are the essential heart of every atom, so it's just as well we've never seen a proton fall apart. But they can't live forever, can they? The Bible of Fundamental Physics, the Review of Particle Physics, devotes several pages to the ways a proton might fall apart. Each decay mode comes with an estimate of how long you might expect to wait to see one of these particles. Bedrocks of the atomic nucleus disintegrate that way. The units are thousands of billions of billions of billions of years. Our stripling universe is a mere 13.8 billion years old. So this is a judicious, scientific way of saying that no one has ever seen a proton decay. It's not for want of looking. A 50,000-ton tub of ultra-pure water under a mountain in central Japan is one place where researchers are watching out for the pop and fizzle of a dying proton. Late last year, the team published, this is another one that was done in 2015, Late last year, the team published its latest estimate for how often one particularly eagerly sought decay mode occurs. At most once every 5.9 times 10 to the power of 33 years. You'd think people would be pleased that the particles we're all made of are stable. Physicists too. Their standard model of particle interactions firmly indicates that protons, as the lightest particles constructed of 3 quarks, should never decay. So why is never not good enough? The answer is that few believe the functional but ramshackle standard model is up to snuff. So-called grand unified theories provide a more coherent account of 3 of nature's forces. Gravity remains aloof at the price of the proton decaying. It's the signal of the grand unified theory, says Benjamin Alanak, a theorist at the University of Cambridge. Not only that, but these ambitious models predict the proton should live for somewhere between 10 to the power of 30 and 10 to the power of 35 years, just the range experiments are now probing. We're entering the really interesting area where you can start to rule these theories out, says Alanak. Or if they're correct, you should start seeing protons decay. It could be a long wait. Pushing the minimum lifetime up to a factor of 10 means watching for 10 times as long. So should we be worried if one of the fundamental components of matter, the stuff that makes up you and me, proves to be a little wobbly? Not really. Our bodies do not make good observatories for proton decay. From my back of the envelope calculation, it would be a rare person that would experience a proton decay in their lifetime, says Alanak, and the universe has so many protons that will be long gone before they run out. In the meantime, here's the best answer we have for the lifetime of a proton: a very, very long time. So this next one: why is ice slippery? Most think it's down to a liquid layer, but can't agree on how it forms. One theory insists it's a super solid skin capable of electrostatic repulsion. For physicists, no less than figure skaters, ice is remarkably hard to get a grip on. The overwhelming consensus is that ice has low friction because of a thin film of liquid water coating its surface. Hence, skaters balanced on thin metal blades can glide smoothly across the ice rink, but grind to a halt on the wooden floor beyond. The tricky part is how this liquid layer forms. More than a century of research has brought us a little closer to the definitive answer. It all started in June 1850, when Michael Faraday told an audience at London's Royal Institution of how pressing 2 ice cubes together led to them forming a single block. He attributed this to the appearance of an intervening film of water that quickly refreezes. For many years, the appearance of this layer of water was put down to pressure. In fact, even a person of above average weight on a single skate generates far too little pressure to account for the observed melting, says Anne-Marie Kietzig of McGill University in Montreal, Canada. The mathematics doesn't work out. Instead, Kietzig argues that the main player is frictional heating. The movement of a blade across the ice, for instance, easily generates enough heat to melt some of it. You might think that would be the end of it, but Chungking Sun of Nanyang Technical University in Singapore has other ideas. He argues that since ice is slippery even when you're standing still, friction cannot be the whole story. Mechanisms such as friction heating and pressure melting have been ruled out, he says. According to Sun, the assumption that the slippery layer coating ice is a liquid is also fundamentally flawed. He says this layer should probably be called a supersolid skin, because the weak bonds between H2O molecules at the surface are stretched. But unlike in liquid water, none of them are broken. He also argues that this elongation of bonds ultimately produces a repulsive electrostatic force between the surface layer and anything it comes into contact with. He compares the effect to the electromagnetic force that levitates maglev trains. What is that? I think they're just fast-moving trains. Maglev trains, or the air pressure a hovercraft generates beneath its hull. If he's right, his model helps to explain many of the layer's properties, including its remarkably low friction. I believe the problem has been completely resolved, says Sun. Most in the ice field are not convinced. Jen Sasaki at Hokkaido University in Sapporo, Japan, who made the first direct observations of this layer in 2013, prefers to call it a quasi-liquid. He thinks it represents a transitional stage between solid and liquid as the temperature goes up. For Sasaki, understanding how this mysterious sheet of H2O forms is still some way off. Even when it comes to something as familiar as slipping on ice, he says, reality is much more complicated than we expected. Clearly. The next one is, what is glass? Another random one. Are any of these surprising you guys? Things aren't as clear as you might think. Glass is a weird kind of solid liquid, and how it comes to be like that defies all explanation. Forget the hoary myths peddled by tour guides at old European churches and cathedrals. Medieval window panes are sometimes thicker at the bottom, not because of the slow flow of glass over centuries, but because of the uneven way molten glass was originally rolled into sheets in the Middle Ages. Glass is not a slow-moving liquid. It's a solid, albeit an odd one. It's called an amorphous solid because it lacks the ordered molecular structure of true solids, and yet its irregular structure is too rigid for it to qualify as a liquid. In fact, it would take 1 billion years for just one of the atoms in a pane of glass to shift it all. But not everything about glass is quite so clear. How it achieves the switch from liquid to amorphous solid, for one thing, has remained stubbornly opaque. When most materials go through this transition between liquid and solid states, their molecules instantly rearrange. In a liquid, the molecules are moving around freely, then snap, they are more or less locked into a tightly knit pattern. But the transition from the glass blower's red-hot liquid to the transparent solids we drink from and peer through doesn't work like that. Instead of a sudden change, the movement of molecules gradually slows as the temperature drops, retaining all of the structural disorder of a liquid, but acquiring the distinctive physical properties of a solid. In other words, in all forms of glass we see something unusual. The chaotic molecular arrangement of a liquid locked in place. The process underlying this strange behavior remains an open question. The number of explanations also matches the number of researchers, says Hajime Tanaka at the University of Tokyo in Japan. One possibility is that it's all down to energy use. According to the laws of thermodynamics, which govern how energy is transferred within a system, every collection of molecules is driven to find an arrangement with the lowest possible energy. But within any given system, some patches do better than others, meaning different groups of molecules settle into different configurations, and overall into an irreconcilably chaotic arrangement. But even if we put it down to thermodynamic laws, it's not clear what exactly drives glass's strange behavior. The push for low energy might be the prime mover. Then again, it could be the irrepressible tendency towards a maximum state of disorder. That's a perfectly plausible proposal, though it raises the troubling question of how ordered solids manage to survive. Tanaka is not giving up just yet. So far, crystallization and glass transition have been studied independently, he says. But Tanaka believes that glass may form in a manner not all that different from crystals, which have proved an easy target for analysis thanks to their repeating geometric structures. If he's right, maybe glass will finally become crystal clear. I'd always heard that glass was sand, or sand was glass. Have you heard that before? Am I getting confused with something else? Here's a good one. Next one is, can we get energy from nothing? It depends what you mean by nothing. Ask a physicist about a vacuum, the very definition of nothingness for most of us, and they will tell you it is pulsing with activity. According to quantum theory, in a vacuum, wave-like fields are constantly fluctuating, producing particles and their antimatter equivalents that fizzle in and out of existence. So even in the depths of interstellar space, there is plenty going on in what we call zilch. This idea leads to some outlandish predictions. In 1948, the physicist Hendrik Casmir proposed that if you place two parallel metal plates close to each other in a vacuum, there will be more quantum electromagnetic fluctuations either side of the plates than between them. Their proximity limits the wavelength of fluctuations in that space, creating a force pushing the plates together. The phenomenon became known as the Casmir effect. It's a weakling force, but it has been detected. And more recently, physicists like Chris Wilson, now at the University of Waterloo in Canada, have tried to prove another eccentric prediction, that it is possible to use the effect to release latent energy. Instead of allowing the fluctuations to tug on the plates, you rapidly... I'm just going to move my leg. It's falling asleep. Instead of allowing the fluctuations to tug on the plates, you rapidly force the plates together to squeeze their wavelengths and force out photons. Trouble is, you can't accelerate even the tiniest mirror to the huge speeds required. So in 2011, Wilson and his colleagues tested the dynamical Casmir effect, as it's known, by using rapidly changing electrical currents to simulate the effect of minuscule mirrors whooshing together at a quarter of the speed of light. Sure enough, a pair of photons jumped out from the vacuum, energy, albeit a piffling amount, from thin air. You can think of it as being like the mirror has knocked the particle into existence, says Wilson. The experiment didn't produce energy overall, generating the currents required more than was produced. But harnessing the Casmir effect remains theoretically possible, and even a small success might go a long way. Engineering the inside surfaces of the mirrors to manipulate fluctuating fields in a different way can create an outward pressure that pushes two objects apart. This reverse Casmir effect could come in handy when making switches for nanoscale devices. For now though, the build-up of an electric charge between moving parts swamps the effect. And that's the least of the caveats. Some physicists still refuse to believe that quantum fluctuations in a vacuum are real. Never mind the Casmir effect and its reversal. Wilson is now refining his experiments to answer the criticism that he simply produced heat energy as a result of the apparatus warming up. And if he can show that the particles generated are entangled as predicted by Casmir, that would provide the most convincing evidence yet that you really can get something from nothing. I'm not too sure I understood a lot of what I was just reading then, but that's why I'm not a scientist. I just closed it down. So what are we up to now? Got 4 left. Why does space have 3 dimensions? But does it? For anyone versed in modern theoretical physics, that's not such a silly question. I don't know any mathematical reason why 3-dimensional space is more consistent than any other number, says Leonard Susskind of Stanford University in California. Susskind is one of the founders of string theory, which is our best stab yet at a unified understanding of physics, and perhaps the best known model in which extra dimensions are found. One of string theory's peculiar features is that when applied to fewer than 9 spatial dimensions, the mathematics goes wild, predicting violent fluctuations that rip apart the very fabric of the universe. But extra dimensions do more than just save string theory's blushes. In a wider set of theories, gravity leaking into a higher space could explain why in our 3 dimensions it is so weak compared with other fundamental forces, and why the expansion of the universe is apparently accelerating. So perhaps the question becomes, why does space have 3 visible dimensions? One idea from string theory is that the universe started out as an infinitesimally small 9D ball of string, but only 3 strands unfurled in its subsequent headlong expansion, leaving the others tucked up tightly in every pixel of our 3D space. Or perhaps our 3D universe exists on one of many brains, membrane-like entities that float around in a larger, higher dimensional space. Lisa Randall of Harvard University and Andreas Karch of the University of Washington in Seattle have shown that brains colliding in such a space would tend to form 3D brains, an explanation of sorts for why we see a universe with 3 dimensions. That's brains like BRANES, not brains. Just in case you're wondering. If large other dimensions do exist, particles escaping into them might take energy from those we see. The Largest Hadron Collider has been looking for the signatures of missing energy, so far without success. Such failures rile Carlo Rovelli of the University of Aix-Marseille in France. The idea that space could have more than 3 dimensions was proposed more than half a century ago, and has delivered more disappointments than results, he says. So we're back to the more basic question, why only 3 dimensions? Perhaps because some aspect of our universe wouldn't work otherwise. The precise degree of quantum weirdness we observe seems only possible in 3D space, for instance, and Susskind points out that in any other number of dimensions, the electromagnetic and gravitational forces would have very different strengths. With fewer than 3 spatial dimensions, for example, gravity does not lead to attractive forces. Atoms, planets, and stars would not form properly, and humans would not be around to ponder the existence of dimensions. Did such a peculiar, curiosity-friendly 3D universe arise as part of a multiverse in which every possible type of universe exists? A possibility espoused by string theory? Or is it just one of a kind? That's a toughie, but either way, we're still a distance away from explaining the essential 3-ness of space, says Randall. I think it would be lovely to have an answer, but as of now we don't. Fair enough. This one's kind of interesting. Why do we move forwards in time? There is a reason we say time goes by. It seems to flow. No matter how still we stand in space, we move inexorably through time, dragged as if in a current. As we do, events steadily pass from the future via the present to the past. Isaac Newton saw this as a fundamental truth. All motions may be accelerated and retarded, but the flowing of absolute time is not liable to any change, he wrote. So how does time flow, and why always in the same direction? Many physicists will tell you that's a silly question. The idea that time can, in some meaningful sense, be said to flow is just a complete non-starter, says Hugh Price, a philosopher at the University of Cambridge. For time to flow, it must do so at some speed. But speed is measured as a change over time. So how fast does time flow? George Ellis, a cosmologist from the University of Cape Town, South Africa, has an answer. 1 second per second. Price says that's meaningless. Even if time was standing still, it could be said that for every second that passes, 1 second passes. Indeed, if that's a measure of flow, we could say that space flows. It passes at 1 meter per meter. Ellis is up against one of the most successful theories in physics, special relativity. It revealed that there's no such thing as objective simultaneity. Although you might have seen 3 things happen in a particular order, A, then B, then C, someone moving at a different velocity could have seen it a different way. C, then B, then A. In other words, without simultaneity, there's no way of specifying what things happened now, and if not now, what is moving through time. Rescuing an object now is a daunting task, but Lee Smolin of the Perimeter Institute of Theoretical Physics in Waterloo, Canada, has given it a go by tweaking relativity. He argues that we can rewrite physics in a way that includes now if we sacrifice some of our objective notions of space. Most physicists aren't having it. The general consensus is that time is more or less just like space, an immutable dimension stretched out through a 4-dimensional block universe. Every moment in that universe has a past, present, and future, says Sean Carroll from the California Institute of Technology in Pasadena. A person is described as a history of moments, and those moments all have a feeling that they're moving from the past to the future. That doesn't answer the question so much as shift it. If time does not flow, what makes us think it does? And then mystery number 9. This is going to be a weird one, I'm sure. Where does quantum weirdness end? In the bizarre reality of the quantum world, particles can be in 2 places at once. Why can't golf balls or milk do the same? Right? We do not find at breakfast that the milk is simultaneously poured onto our cornflakes and not, says Andrew Briggs, a physicist at the University of Oxford. Nor can you be in 2 places at the same time, no matter how hard you try, none of which is even remotely surprising. Until that is, you consider that the laws of quantum mechanics insist that subatomic particles such as electrons routinely pull off such a feat. So if electrons can pop up in multiple places at once, why can't milk and humans, essentially collections of fundamental particles, do the same? Here we have to start small. This particular brand of quantum weirdness is best illustrated by the double-slit experiment, where you would fire a beam of electrons, one after another, at a screen containing 2 slits. You would expect the electrons to pass through one slit and hit the detector placed behind the screen at a single point every time. But reality isn't always that straightforward. When researchers don't keep track of each electron's path, the beam passes through both slits simultaneously in the same way as a light wave, creating a pattern of bright and dark stripes on the detector that is characteristic of 2 overlapping wavefronts. So electrons can exist as both waves and particles at the same time, a phenomenon known as wave-particle duality. As if that wasn't weird enough, when researchers monitor one of the slits, the interference pattern disappears. Electrons suddenly abandon their wave-like behavior, preferring to travel through one slit and produce a single spot on the detector. That's probably always the weirdest part of quantum physics, is like things change when they're observed. Physicists explain this by invoking the wave function, a mathematical widget that describes the probability of finding a quantum object in a particular state or location at any given time. When the particle is measured or disturbed in some way, its wave function collapses and it snaps into a single state and a definite position. This collapse can be triggered by an interaction of a quantum object with its environment, a rogue vibration, for example, or a heat fluctuation. That leads us to an unsettling conclusion. Isolate a molecule even hundreds of thousands of times the size of an electron sufficiently from its environment, and there's a chance it might still be existing in its uncollapsed quantum state. Indeed, researchers have now spotted improbably large objects, including tiny resonating strips of metal visible to the naked eye, existing in two states at once. Even so, it's pretty clear that once something gets large enough, it throws off its quantum properties. As Erwin Schrödinger noted, it's absurd to say a cat can be both dead and alive. So how large can quantum weirdness go? Do you know the Schrödinger cat experiment? Some physicists would say that the size limit depends on the size of your checkbook, says Briggs. With a sufficiently sophisticated experiment, he argues, researchers could reliably screen out disturbances from the environment ever more finely to show ever large objects obeying quantum rules. Together with colleagues at Oxford, Briggs is testing the limits of quantum behavior more rigorously than any experiment to date. The challenge is to find ways to place bigger things in fuzzy quantum states that are less sensitive to outside influences. But Briggs does not expect to solve the conundrum anytime soon. That's partly down to the difficulty of defining a system in quantum mechanics. Strictly speaking, anyone or anything observing quantum interference becomes part of the system, making it tough to draw conclusions about the size at which quantum effects vanish. You can always argue that you, the observer, are in superposition too, says Briggs. And lastly, this one relates to all of us, really. The last one is how creative computers will dream up things we'd never imagine. On a summer's day in 1899, a bicycle mechanic in Dayton, Ohio, slid a new inner tube out of its box and handed it to a customer. The pair chatted and the mechanic toyed idly with the empty box, twisting it back and forth. As he did so, he noticed the way the top of the box distorted in a smooth spiral curve. It was a trivial observation, but one that would change the world. The shape of the box just happened to remind the mechanic of a pigeon's wing in flight. Watching that box flex in his hands, Wilbur Wright saw how simply twisting the frame supporting a biplane's wings would give him a way to control an aircraft in the air. Serendipity and invention go hand in hand. The Wright brothers' plane is just one of many examples. Take Velcro. George de Mestral invented the material after he noticed the hook-covered seeds of the burdock plant sticking to his dog. And Harry Coover's liquid plastic concoction failed miserably as a material for cockpit canopies, as it stuck to everything. But it had a better use, superglue. It may be romantic, but it's an achingly slow way to advance technology. Relying on happenstance means inventions that could be made today might not appear for years. The way inventions are created is hugely archaic and inefficient, says Julian Nolan, CEO of Iprova, a company based in Switzerland which specializes in generating inventions. Nothing has changed for hundreds of years, he says. That's totally out of sync with most other industries. But we are starting to make our own luck. Those eureka moments could soon be dialed up on demand as leaps of imagination are replaced by the steady steps of software. From algorithms that mimic nature's way of producing the best designs to systems that look for gaps between existing patented technologies that new designs might fill, computer-assisted invention is here. The impact could be huge, Some claim automated invention will speed up technological progress. It could also level the playing field, making inventors of us all. But what happens if the currency of ideas is devalued? To qualify for a patent, for example, an idea can't be obvious. How does that apply when ideas are found by brute force? The first group to mimic evolution in patent design, pioneering the use of so-called genetic algorithms, was led by John Koser at Stanford University in California in the 90s. The team tested their algorithms by seeing if they could reinvent some of the staples of electronic design. The early filters, amplifiers, and feedback control system developed at Bell Labs in the 20s and 30s. They succeeded. We were able to reinvent all of the classic Bell Labs circuits, says Koser. Had these techniques been around at the time, the circuits could have been created by genetic algorithms. In case that was a fluke, the team tried the same trick with 6 patented eyepiece lens arrangements used in various optical devices. The algorithm not only reproduced all the optical systems, but in some cases improved on the originals in ways that could be patented. Just looking through this article, it's really long. I'm going to skip ahead a little bit because I don't think it even really matters. Let's get to the point, Human inventors who use automated innovation will leapfrog those who don't. But where do we draw the line between the two? I don't think there is a clear separation between human and algorithm, says Eric Bonobo, founder of Ecosystem, a company based in Cambridge, Massachusetts. The key is to find the right division of labor. Ecosystem uses genetic algorithms to optimize everything from inventions to business processes, an approach Bonobo calls enhanced serendipity. However, if the division of labor is too much on the computer's side, it could undermine the patent system itself. Currently, a person having ordinary skill in the art must believe that an invention isn't obvious if it is to be granted a patent. But if inventors are only tending a computer, the inventions that arise could be deemed an obvious output of that computer, like hot water from a kettle. These concerns have already been raised with drug discovery. If drug discovery tools become so powerful that a researcher is just overseeing the tool's activity, does that make the whole process obvious and so not patentable? Industry could be shooting itself in the foot by developing such technology. Another concern is that broad access to smart invention tools could speed up human technological development, making the resulting gadgets may consume Earth's resources all the quicker. McCaffrey is more optimistic. I'm really impressed with the engineers who are creating ways to improve housing, food storage, crop growth, water purification, and transportation in the developing world, he says. I sincerely hope we use this emerging invention assistance technology to address the really important problems faced by humanity. Chance favors the prepared mind. If Wilbur Wright hadn't been thinking about his problem, he may never have had his eureka moment. Automating that amounts to making accidental encounters orders of magnitude more efficient, says Bonobo. In other words, outsource serendipity to the algorithm. Anyway, that is the end, guys. Some of those were a bit easier to understand than others, weren't they? But then not really at the same time. Take something as simple as ice being slippery and then have a big discussion about why. Anyway, I will keep looking through this website over the coming weeks and see if I can find some other interesting ones to read to you. So I hope that you'll like that. And thanks for watching, guys, and hello to all the new subscribers that have signed up recently. And I will see you guys in the next video. Bye. Hey guys, welcome back to another video. You might think this one looks very similar to the fact video about mountains because I decided to try recording a couple of videos in a row so I can pump out a bit more content. But this is a different video. So sometimes I'm browsing around online, just killing time. What do they call it? Death scrolling through things. And I might come across a post or a video or something that seems to connect with a lot of people. And I found one like that on Reddit. Maybe I'll call this like relatable Reddits or something. I think the Reddit page is called Ask Women. I'm not actually sure if it's all women responding or if it's just, it could be a guy asking the question, I don't know. I'm sure we can all relate to this. The question that was asked was, have you ever had intense chemistry with someone but couldn't be together? And it has over 150 responses, so a lot of people related. I'm not going to read all the responses. It's more my hope that maybe listening to some of these responses will maybe make you feel less alone, especially if you're going through something like this right now. So let's get into it. So the first person comments, one of my friends I have intense chemistry with. I think it's because he's intelligent and sexy, and when I first met him, I wanted to be with him even though I had a boyfriend. His girlfriend was even cool with it, but I realized I would have a better life with my boyfriend. Then my boyfriend and I broke up, and I found a sexy British dude. Always go for the sexy British dude. And then someone else commented underneath, co-signing this as the girlfriend of a sexy British dude. Someone asked, quick question, is he sexy because he's British, or is he sexy and British? And the poster says, he's already sexy, but the British accent is like the cherry on the sexy sundae. So big shout out to anyone who's listening that's British. I'm just scrolling through. Okay, this is a cute one. I had insane chemistry with a woman I met online in a random fan community on LiveJournal. She was married and lived on the other side of the country, and we weren't expecting to be anything more than friends. But apparently we are not capable of being platonic with each other. After 11 days of increasingly flirtatious conversation, I told her we couldn't talk anymore because she owed it to her husband to talk about why she was so deeply unhappy in her marriage and to try to work things out without my interference. Then I was an emotional wreck for days. It felt like the world was ending. Even though we barely knew each other, I staggered through exam week in a haze of exhaustion and misery, and classmates and co-workers who weren't even acquaintances asked if I was okay. A week after I cut contact, she broke the silence to tell me she decided to get a divorce, and she was sleeping on a friend's couch for a while. I responded briefly and wished her well. I lasted for another week of obsessively rereading our texts, emails, and instant messages. Then I emailed her on some flimsy pretext. We did a careful dance of email-only platonic conversation for about 6 weeks. Both of us put hours and hours into crafting long, rambly emails that were deliberately not flirtatious. But there was still an undercurrent. Then she asked if she could come and visit me while she was on a planned trip to my side of the country. I almost hyperventilated, but I knew instantly that I was going to say yes. She came to visit. The chemistry was unbelievably intense. We started dating long distance. Exactly 0 of her friends and family were surprised that she turned out to be gay, and several of them told her that they'd been surprised and skeptical when she married a man, She was like, "Now you tell me?" A year later, I moved across the country to be with her shortly before her divorce was finalized. 7 years after that, we got married. I'm so grateful that I had the guts to break things off and let her resolve her marriage without my interference. I hated myself for helping her have an emotional affair, and I knew it wasn't right. Cutting contact for that short time and keeping it just friends for a while let us both feel better about how our relationship got off the ground. The next commenter says, 50% he had commitment issues, 50% a relationship would be challenging long distance, and he didn't want to put in that effort. Chemistry and compatibility aren't the same thing, and you/I can't be compatible with someone who doesn't really want a relationship. It's unfortunate and made me feel disappointed, but nobody's ideal relationship is like, I would love to be with someone who likes me but doesn't really want to commit to me, so it's not a loss. Another one says, yes, but we couldn't be together because we live too far apart. We're both people who value long-term monogamous commitment, our careers, our friends, and our families, and we couldn't see a future together where we could respect all of those values. One or both of us would have to move and leave our lives behind. Yes, the reason I was 16 and he was 21. I was in love with him, but he had a ton of issues he needed to work out. How did I get over it? I cut myself off from it. It was incredibly painful and hard, but I knew I had no other choice. He was never going to choose me, and in the long run I was glad he didn't. It took me 2 years to say I was fully over it. Yes, we disagreed on everything, and I mean everything. Anything I loved, he found to be in poor taste, and vice versa. We basically agreed that we are insanely incompatible, so we became friends, more like frenemies with benefits. The next one says, yep, the timing wasn't right. It was socially complicated. He probably would have lost his close friends if we'd gotten together. Despite that knowledge, we carried on an intense flirtation for months. At one point I realized I didn't want to invest energy into someone that wasn't interested in pursuing me back. That helped me get over it for about 3 weeks, until I actually saw him in person again and the chemistry was still there. So then I applied my favorite solution for getting over a crush: get rejected. I leveled with him that I enjoyed our flirtation, but I hoped it was going somewhere. He was upfront that it was not. Previously, when we talked about the future more obliquely, he always kind of dangled statements that I took as not right now, rather than no. I went a few weeks without talking to him to help me recalibrate, and now we're friends again, with better boundaries. And that's it. With that perspective, the chemistry mostly died. If he's not interested enough to make something happen, then he's not for me. The end. There are other people who will be interested and will not have to be convinced or persuaded. They might even pursue me. Online dating helped with that. It's hard to feel too hung up on one person that won't be with you when there's a line of people clamoring for a shot. I had great chemistry with a co-worker at a summer job once. He had a girlfriend at the time, but I think they broke up shortly after. A couple years later, we got back in touch. This time he was single and I was in a long-distance relationship with my future husband. We hung out a bit and he told me that he had a thing for me the whole time we were working together. I told him the feeling was mutual and was very tempted to hook up, but didn't. It was the only other person I thought I might have ended up with had things been different. But I like things difficult and decided to jump through hoops and marry someone from another country, move across a few continents, and deal with loads of immigration BS, rather than marry someone who grew up a few towns over. I've been happily married 7 years now, and I think he got married recently. Sometimes you just have to make a decision and stick with it. There are billions of people out there. It's not that unusual to meet more than one person you feel you could have made a life with. But the value of a long-term relationship lies in trust and commitment, not just attraction and compatibility. We're not really in touch beyond being Facebook friends, but he's a good person and I hope he's happy in his relationship. We were both in relationships, so we both decided to cut off contact with one another because we didn't want to indulge in it. Things had started to become flirty and I just didn't want to go there. Another time was because I actually didn't like a lot about him, but the chemistry between us was pretty unreal. Chemistry alone is not enough to get involved with someone, so I moved on. Someone else says, yes, I was in a relationship, so I couldn't act on it. Flirtation and desire are powerful forces. To this day, I still have a mental what if. Yes, he was 20 years older than me and a family friend. I just couldn't do that age gap or deal with my family's scrutiny. I still wonder what if. Someone says yes, sad face. The timing was never right and the universe conspired against us constantly. Someone else says, my long-distance relationship with this someone just ended. He has mental issues due to a pretty crazy past and can't be with me while working on them. I'm so hurt because I would do my best to help, but apparently I won't be enough. He needs to be alone. Someone says, short comment, he was way too intelligent for me and thought I wasn't smart enough for him. Oh well. Yes, but chemistry unfortunately does not always mean compatibility. We were too different and we had a tumultuous relationship. The kind that is exhausting and it's very high highs and very low lows. You try to make it work because how can two people so insanely attracted to each other not work out? Unfortunately, it just became too unhealthy emotionally. Now I'm in a happy, healthy and stable relationship, and in retrospect, know 100% it was the right choice. Yep, we were together, so I thought, for 6 months, and his inability to commit / not talk to other women broke us apart. He still comes around talking about getting back together, etc., but I can't do it. He doesn't understand. I can't help that. At the beginning it was perfect. We were both happy, but the mask started to slip and the problems started to creep in. I tried for 6 months to jam a square peg in a round hole, as it were, and it wasn't working. Someone says, I hate when I get that vibe feeling with strangers and I know neither of us is ballsy enough to do anything about it. And someone else says, thanks for whoever started this thread. I'm currently going through a really tough time with a guy I can't be with, and it's really comforting to read other people have been through similar and gotten out the other side. I think the original poster says, I was thinking the same thing. I was not expecting to see so many responses. Glad I could help a bit. Someone said yes. My long-distance best friend. I met her through a girl I would go on to date later on, and we circled each other for a few months. It drove me absolutely insane because our chemistry was like nothing I'd ever felt before or since, and I knew she felt the same way, but she was pretty elusive and it was a bit crazy making. I tried to move on and began dating the mutual friend while we settled into a friendship. And she moved a few states over a few months later, which I found out later was the reason she'd been so avoidant, because she knew she wasn't staying and tried to bury her feelings. It's been a few years now. She's helped me through a lot of crazy stuff. I go visit her a few times a year and she comes down a few times a year. I've been dating someone for about 3 months now, and at this point I'd firmly slot my feelings for my friend as platonic, as I have no interest that's sexual or romantic at this point. It just took time. That said, I've never met anyone that makes me come alive the way that she does, and saying bye for 3 to 4 months at a time is always hard and kind of painful, to be honest. He was a close friend. We were pretty much dating, but not calling it for what it was. I wanted a relationship, and he admitted it would only progress into a physical relationship. It was easy to get over it because I knew I was beating a dead horse. However, it's crazy because sometimes when we reconnect, the thought that we would have been good together still crosses my mind, but I don't dwell on it, especially because chemistry alone will not save any kind of relationship. Someone says, "Wow, I didn't realize how much I needed this thread." The most insane chemistry I've had with a person I met was when I was still trying to make it work with an ex, and he was single. I left for a summer and came back to work. Ex and I broke up eventually, but by then he got a girlfriend. He's still with her today and we still work together, and I still have feelings for him that are impossibly strong. We're not meant for each other. We're different people with different interests. I can't leave my job because of a dumb guy, and I just started seeing someone who is 100% right for me in every way, who I consciously choose every day. It's relieving to see so many people here say that chemistry isn't always the right reason to be with someone. Anyway, I kind of want to keep reading these guys, but I'm hearing some noise in the background, so I'm thinking I might just call it here. But if you like this, let me know and I can make a part 2. Thanks for tuning in, guys, and I will see you next time. Bye. Hey guys, how are you? I have got for you today some articles all about the universe, some science articles and physics articles, things about black holes and interesting questions that scientists like to think about. These articles are all from the New Science website that I got a subscription to. It's almost done, so I might continue with it because it's been pretty good so far. Or I might try to find a different website to read things from. I'll probably come back to it anyway at some point. It's raining in the background too, if you guys can hear that. It doesn't sound too loud in my house, but I can really hear it picked up on the microphone, so it probably just sounds a bit like white noise. But I think it's going to be raining all week, so there won't be any other better time to record this. Anyway, let's get into it. What I've been doing with these articles is putting them through ChatGPT to rewrite them, just so I'm not hopefully breaching any copyright, but I'll still link to the articles anyway, just if you're interested in reading more. So the first one I have for you is called "Why This Is a Golden Age for Life to Thrive Across the Universe." Nearly all the stars that will ever exist have already been born, and they've been around long enough for life to evolve on planets orbiting them. Since the universe began 13.8 billion years ago, it has hosted a variety of cosmic entities, stars, planets, moons, and quasars. If you get restless at long performances, the cosmic show is far from over. it's expected to continue for at least another 100 billion years. This raises an intriguing question. Are we currently living at a pivotal moment in the universe's history, or is this just a routine scene in an extended plot? One clue that suggests this is a significant moment is found in the fundamental constants of the universe, such as the strength of gravity and the fine structure constant known as alpha. These constants dictate how matter and light interact, influencing how stars burn. If these constants were even slightly different, life as we know it might not be possible. Why do these constants appear so perfectly tuned? One hypothesis is that they are not truly constant and may have changed over the universe's lifespan. John Webb at the University of Cambridge has explored this idea, particularly concerning alpha. Previously, Webb claimed alpha has changed based on precise cosmic measurements. However, he now believes these claims were incorrect due to systematic errors in the instruments used to collect the data. The existing measurements are close to meaningless, Webb states, but he remains hopeful that advancements in artificial intelligence and new instruments like the James Webb Space Telescope will soon provide accurate data. Despite this optimism, most physicists dismissed the idea that the constants of nature have changed or that our universe is exceptional. Alexander Vilenkin from Tufts University in Massachusetts advocates the principle of mediocrity, suggesting there is nothing particularly special about our universe. Nonetheless, we might still be living at a unique moment in cosmic history. Life as we know it couldn't have formed without stars to provide energy and planets situated at favorable distances from these stars. Moreover, life couldn't arise immediately after stars first appeared. It needed heavier elements than the hydrogen and helium of the first stars to support complex biochemistry. Several generations of stars are needed to build these heavy elements up to a level where you get planets and the chemistry of life, explains Geraint Lewis at the University of Sydney, Australia. This process took at least a few billion years post-Big Bang. Being intelligent enough to comprehend this cosmic timeline also requires specific conditions, which are becoming scarce. Significant intelligence seems to take billions of years to develop, at least it did on Earth, and the star formation that can support such development is declining. More than 95% of the stars that will ever exist have already been born, says Lewis. Star formation is winding down. In the future, stars like the Sun will become rarer and rarer. In 100 trillion years, all stars will have died, and the possibility of habitable environments will vanish. That marks the end of the cosmic show, plunging the universe into infinite darkness. Practically, we have even less time. The mysterious force known as dark energy is likely to drive the universe apart long before that, making it impossible for light from other stars to reach Earth. Even if life could still exist, conducting astronomy would become impossible. Thus, we are part of a unique generation of humans who can explore and understand the cosmos. We truly live in a special time in the life of the universe, Lewis remarks. The next one is called Why You Should Feel Comforted, Not Scared by the Vastness of Space. Some find the universe's immense scale terrifying, but here's why it should bring you comfort. One chilly evening last October, I stepped into my garden to look look at a faint, blurry spot in the night sky. To the naked eye, it's almost invisible unless you're in a very dark location. Through binoculars, it transforms into an elongated smear with a bright core, the Andromeda Galaxy, the most distant object visible to the unaided eye. I frequently observe Andromeda during winter. However, on October 6th in 2023, the occasion was special. It marked 100 years since Edwin Hubble made the observations that would later reveal Andromeda as a galaxy separate from the Milky Way. As I stood there, I marveled at the light that had traveled 2.5 million light years to reach me. Many people find the universe's vastness overwhelming, feeling tiny and insignificant. However, there are two reasons why this vast scale should not induce fear, but rather offer comfort. First, the immense scale of space provides a refreshing perspective. For me, learning about the universe's enormity has always been a source of solace. When faced with daunting tasks like public speaking, I remind myself of the universe's size, which makes my challenges seem less intimidating. If life feels really overwhelming, I just remind myself like I'm just a little speck in the grand scheme of things. My life is really short in the grand scheme of things too, so maybe I shouldn't dwell on anything, no matter how significant it seems at the time. Others share this sentiment. Journalist Oliver Berkman, for instance, describes this mindset as really relaxing. In his book 4,000 Weeks, he introduces the concept of cosmic insignificance therapy, emphasizing that our actions in the grand scheme of things hold little consequence. The second reason comes from philosophical reflections on cosmic insignificance. Philosopher Nick Hughes from the University of Oslo notes that contemplating the universe's vastness highlights our limited control over its grand trajectory. While this realization can initially seem bleak, Hughes argues it's not a reason for despair. Power, he explains, is only valuable as a means to an end. The things we truly value, relationships, justice, knowledge, art, don't require cosmic scale power. Most of what matters to us is within our grasp, Hughes says. Though Hughes admits to feeling anxious about our small place in the universe, he also finds it highlights our existence's fragility and preciousness. This sentiment resonates with me as well. Feeling small in the vast cosmos reminds me to cherish every moment of life. Whenever I need a reminder of this perspective, Andromeda is there to provide it. This one sounds interesting. I think there's a couple of articles that are talking about this. So this will be the first one. It's called "The Universe is Built a Lot Like a Giant Brain, So Is It Conscious?" Research reveals a striking structural similarity between the universe and the human brain. Does this suggest that the cosmos has its own form of consciousness? An astrophysicist and a neurosurgeon walked into a bar. This isn't the start of a joke, but the beginning of an intriguing scientific comparison. Years ago, astrophysicist Franco Vezza reunited with his childhood friend, neurosurgeon Alberto Filetti. During their conversation, Vezza, who worked the structure of the universe, and Filetti, who studies the brain's composition, wondered if there were similarities between their fields. That almost sounded like thunder. Must be a storm or something. I don't think this will last for the entire video. Vezza, based at the University of Bologna in Italy, took this curiosity further. He used statistical techniques to compare neurons in the brain's cortex with the cosmic web, the large-scale pattern of matter in the universe. He analyzed the number of nodes and the density of connections in each network. The results were surprising. The similarity is quite striking, Vesa says. Despite the vast difference in scale, 27 orders of magnitude, the patterns in both the brain and the universe showed a remarkable overlap. For some physicists, this similarity is too significant to ignore. It's even led to suggestions that the universe might think or possess some form of consciousness, a concept rooted in the philosophical idea of panpsychism. Historically, consciousness has been explained in two main ways. Materialists argue that consciousness arises purely from physical matter, while dualists believe in the existence of both physical and conscious substances. Both approaches have their challenges, particularly in explaining how consciousness emerges from inanimate matter. Panpsychism offers a different perspective, proposing that consciousness is a fundamental aspect of reality, present in all matter, even at the particle level. This view suggests that human consciousness is built from these basic conscious units. It's gaining popularity, says Joanna Leidenhag, a philosopher who studies panpsychism at the University of Leeds in the UK. Extending this idea, cosmopsychism suggests that the universe itself might be conscious. Vasa, however, is skeptical. Consciousness is already a poorly defined concept, so attributing it to the universe is quite odd, he says. His research was aimed more at understanding how complex networks form, rather than proving the universe's consciousness. He points out that structural similarity doesn't equate to functional similarity. A living brain and a dead brain, for instance, have the same structure but vastly different characteristics. Additionally, the vastness of the universe means any thought would be incredibly slow, given the time it takes for light-speed signals to travel across it. In his book, Why? The Purpose of the Universe, philosopher Philip Goff offers a nuanced view of cosmopsychism. He suggests that since physicists consider particles as expressions of quantum fields, these fields could be seen as fundamental units of consciousness. Goff doesn't claim the universe is capable of reflective thought, but speculates that a fundamental consciousness could influence the universe's evolution. Whether these ideas hold any empirical truth remains to be seen. For now, the rise of panpsychism might reflect more about our changing societal views than about the universe itself. During the Industrial Revolution, we saw nature as a machine. With the digital revolution, we likened the brain to a computer, Leidenhag notes. Now, as we become more ecologically aware, it's not surprising that we're turning to more organic metaphors. This shift in thinking may suggest a broader cultural and philosophical response to our growing understanding of and connection to the universe. I have to look more into panpsychism and cosmopsychism. I think it should be interesting. Next article is called "This Mind-Blowing Map Shows Earth's Position Within the Universe." I did take a screenshot of it so I can put that on the screen while I'm reading this one. This extraordinary map depicts the circle of the cosmos that encompasses us, stretching out to a distance of 200 million light years. At this scale, space is made up of galaxy clusters and voids, the latter being regions with relatively few galaxies. The Milky Way, located at the center, is part of the local group of galaxies with the Virgo cluster as our nearest neighbour. The Milky Way's spiral shape is defined by two primary arms, Scutum Centaurus and Perseus. They sound like Greek names. I've been interested in the Romans and the Greeks, and just learn more about the history. But I know I'm going to struggle a lot with pronouncing all the names. I suppose it'd be good for me to learn. Additionally, it contains a dense region known as the central bar. Our solar system is situated on a smaller structure called the Orion Spur. While understanding our metaphorical place in the universe is complex, astronomy provides a clear picture of Earth's physical position. Earth orbits the Sun at a distance of 150 million kilometers, and the Sun orbits the center of the Milky Way. Specifically, we are located in the Orion arm, approximately 26,500 light years from the galaxy's center. The Milky Way itself is part of the local group of galaxies, which includes Andromeda, our closest neighboring galaxy, situated about 2.5 million light years away. Currently, we are moving towards Andromeda at over 100 kilometers per second, and in roughly 4 billion years, the two galaxies will collide. It's crazy when you hear those kind of numbers. 100 kilometers per second. Somehow you'd think you'd feel that, you know? This collision will disrupt the local group, but it will hardly register in the broader cosmic context. The local group resides on the edge of the Virgo supercluster, a larger structure named after our adjacent Virgo cluster. The Virgo supercluster is one of 4 segments of an even larger supercluster known as Laniakea, which contains approximately 100,000 galaxies. All of this is situated at the center of the observable universe, which may extend far beyond what we can currently see. Despite our ability to chart our place in the universe, there are limitations. We cannot move from our position in the universe to observe it from a different vantage point. Consequently, there are parts of the universe we can never see. For instance, the center of the Milky Way is crowded with stars and dust, obscuring about 20% of the sky, an area referred to as the zone of avoidance, or more accurately, the zone of galactic obscuration. While we can peer through this zone using radio wavelengths, a significant portion of the sky remains hidden, even from the most advanced telescopes. The observable universe contains around 10 million superclusters and at least hundreds of billions of galaxies. While it's impossible to study all of them, we can appreciate the incredible diversity within our own modest corner of the cosmos. Next article is called Why Our Location in the Milky Way is Perfect for Finding Alien Life. Our particular location in the Milky Way is teeming with older, metal-rich stars. New research indicates these stars might offer the most favorable conditions for life to develop on their planets. All known life in the universe exists on a small rock orbiting a star in the minor arm of the Milky Way. With billions of planets that could potentially support life, how does our specific position affect our chances of finding it? Our search for extraterrestrial life has just begun, and we've barely explored a tiny fraction of space around our sun. Jesse Christensen, an astrophysicist at the California Institute of Technology, notes, "The bubble of space that we've managed to search around our sun is very small compared to the size of the galaxy. Despite this, over 5,000 exoplanets, planets orbiting stars outside our solar system, have already been discovered. While some are found throughout our galaxy and even in others, most are located within a few hundred light years of our sun, which is relatively close in cosmic terms. Astronomers are now examining various types of stars in our galactic neighborhood to understand how they might influence the habitability of the planets around them. We reside in the Orion arm of the Milky Way, which is part of the galaxy's main plane, known as the thin disk. Surrounding us are stars within the Orion arm, with the dense core of the galaxy on one side and the sparser outer regions of other arms on the other side. Stars in the thin disk, like our Sun, are rich in metals, elements heavier than helium. Jasper Nielsen, an astronomer at the University of Copenhagen, Denmark, explains they have more iron, magnesium, and so on. In contrast, stars located above and below the plane of our galaxy are part of the thick disk, while those at the galaxy's outermost edge belong to its halo. These stars are typically metal poor, as they were among the first to form in the galaxy, created before supernovae. The explosions of stars that generate heavy elements had enriched the galaxy. This metal richness in our vicinity is promising for the search for life. Nielsen and his team have discovered that planet formation around older, metal-poor stars is challenging due to the lack of material. Conversely, metal-rich younger stars, like those near us, have an abundance of material, allowing them to form a diverse array of planets, including rocky worlds like Earth and larger planets. While our location might not hinder the discovery of life, it poses significant challenges for communication. The vast distances involved make it difficult. For instance, Proxima Centauri, our closest star, is 4.2 light years away. Communicating with potential intelligent life on one of its planets would take nearly a decade for a message to be sent and received. The problem intensifies with more distant stars. Currently, the focus is on finding Earth-like planets. NASA is developing the Habitable Worlds Observatory, HWO, set to launch in the 2040s, with a primary goal of imaging 25 Earth-like worlds around Sun-like stars. Christensen is optimistic, stating, "I believe in our lifetime, something like HWO will see a signal in the atmosphere of a rocky planet in the habitable zone of a star, like our Sun, that we think is life." Just as Edwin Hubble's discovery of Andromeda as a separate galaxy in 1924 revolutionized our understanding of the universe, finding extraterrestrial life could fundamentally change our perspective. Christensen suggests it could spark a revolution in life, religion, philosophy, and science. Or perhaps it might just be a fleeting headline, quickly fading as people return to their daily lives. Yeah, it would be a big deal. Some people would become obsessed with making contact. But the rest of us would, we still have our lives to lead and problems to deal with. So I could see that it becoming a thing that we know, and then life returning to somewhat normal. It would make waves with religion, I suppose, too. Yeah, never know. Next article is called "Is it possible to fully understand the universe while living in it?" Through scientific inquiry, we aim for an objective understanding of the universe. However, many physicists now believe this goal might be inherently unattainable. Science, despite its imperfections, remains our most reliable path to objective knowledge. It employs observation, experimentation, and mathematical modeling to achieve a detached third-person perspective. This is especially evident in physics, which seeks to explain phenomena on every scale. I just had to move my setup into another room because there was a bit of noise going on in the background. So continuing on, just find my spot. We were at, as Jenan Ismail, a philosopher at Johns Hopkins University, puts it, we take ourselves out of the system to stabilize it as an object that we can think about. This approach began in the 16th century with Galileo Galilei, who demonstrated that the movements of celestial and terrestrial bodies could be described using mathematical laws. This method has undeniably succeeded, enabling physicists to construct a robust framework of ideas and equations that accurately predict reality from the universe's grand evolution to the minutiae of elementary particles. Recently, however, a growing number of physicists have started to question the notion of an objective universe independent of our observation. Marcelo Glaser, a cosmologist at Dartmouth College, warns, we get so excited about our capacity to abstract and extrapolate that we forget that physical models are not reality. He argues that failing to recognize our subjective experience as part of the universe can lead us astray. Our models are products of our insider's perspective, not exact representations of reality. The limitations of an objective viewpoint are most apparent in quantum mechanics, the field that governs subatomic particles. Quantum theory, backed by numerous experiments, indicates that a particle's position is only determined when it's measured. Different experimenters can obtain different results from the same measurement. Quantum theory is really screaming at us that observers matter, that facts are relative, says Daniel Areti, a theorist at Ludwig Maximilians University in Germany. This relationship between our minds, our models, and the world is intricate and subtle. This perspective challenges the pursuit of a theory of everything, a set of equations that explains the universe in its entirety. Glaser, along with astrophysicist Adam Frank and philosopher Evan Thompson, explores this idea in their book The Blind Spot. They argue that physicists' overconfidence in mathematical laws hinders our understanding of the universe and our place within it. We mustn't forget that these tiny characters, we ourselves, are also the authors of the narrative they write. Areti echoes this sentiment, stating that trying to understand the mind of God is an outdated view. Instead, he suggests that we can only understand the universe from within, emphasizing the importance of reconciling different observational perspectives. The best we can hope for is that every observer, with its own perspective, is capable of determining what is seen from all the other perspectives by being able to translate between perspectives and not have anything left untranslatable. This approach suggests we might need to move away from the idea of a single objective reality. Areti views reality as intersubjective, lying in the information that relates different perspectives to each other. Similarly, Glaser advocates for systems thinking, which understands the world's complexity through the interconnections between its parts. He believes that a better grasp of emergence, where properties that don't appear in individual components become evident when viewed as a whole, could be key. This new perspective on cosmology would differ significantly from the current approach, resembling the study of biospheres more than black holes. It's a different ballgame, Glaser notes. One clear conclusion emerges, as Ismail states: if you're asking a question that demands an external view of the universe, then you're not asking a question that makes sense. This paradigm shift suggests that our understanding of the universe must incorporate our role within it, recognizing that our perspective is inherently embedded in the fabric of the cosmos. The debate on whether space and time are intrinsic components of the universe or merely emergent properties resulting from quantum entanglement is one of the most profound questions in physics. Recent advancements suggest we may be nearing a breakthrough in understanding. Traditionally, we view space-time as the fundamental framework of the cosmos. However, its true nature, whether it's a basic constituent of reality or a derivative phenomenon, is a topic that continues to perplex physicists. According to Marika Taylor from the University of Birmingham in the UK, this is not just a theoretical curiosity, it impacts practical calculations in physics. A useful starting point for exploring this question is quantum mechanics, which governs the behavior of particles at the smallest scales. One of the theory's most striking features is entanglement, where particles remain interconnected, influencing each other's states regardless of the distance separating them. This principle challenges our conventional understanding of space and time. Cosmologists have increasingly embraced the idea that quantum entanglement might be crucial to the formation of space. By quantifying the degree of entanglement between particles, it's possible to deduce the distance between them. Extending this concept to a network of numerous particles could give rise to a spatial geometry, suggesting that space itself might emerge from quantum entanglement. Further insight comes from string theory, which posits that the dynamics within a given space can be entirely described by information encoded on its boundary, a concept known as holographic duality. Combining this with quantum entanglement could potentially construct a universe with spatial characteristics, including distances and geometric structures. Mathematical physicist Spiridon Mikalakis, along with colleagues Sean Carroll and Charles Cow, has developed a compelling model of space-time's origins. Their theory proposes that entanglement among boundary particles creates a notion of distance, which translates into geodesics, the paths the particles follow through the universe. These geodesics form the geometry of space-time, akin to the curved space described by Einstein's general theory of relativity. Entanglement becomes curvature, and that curvature can be thought of as geometry, Mikalakis explains. However, this approach does not fully resolve the fundamental question of why space and time exist. As Taylor points out, positing that space and time emerge from the boundary of space-time merely defers the issue. We haven't, in a deep sense, explained why space should exist, she notes. An alternative perspective comes from Chiara Marletto at the University of Oxford. Working with others on constructor theory, Marletto seeks to redefine the laws of physics in terms of possible transformations within physical systems, reducing everything to quantities of information. Given that the universe operates much like an information processor, constructor theory aims to provide an information-centric explanation of space's origins. According to Marletto, we would say that time is not fundamental, and space-time is not fundamental either. Nonetheless, these ideas remain under development. A more comprehensive understanding is likely to emerge from studying cosmological phenomena, particularly black holes and the singularities at their centers. As Taylor emphasizes, the whole notion of space-time breaks down there, and understanding how it breaks down is intimately linked to the question of how it emerged in the first place. By unraveling the chaotic behavior within black holes, we may ultimately discover how the three spatial dimensions arise. So you guys, I might leave the video here for the moment, but I have many more articles to read on this topic, so there will be a part 2 to this video. Yeah, I'll leave that with you for now, and I will see you next time. Hey you guys, welcome back to this week's video. I'll be reading some more articles to you today. I found one from the same website as last week's video, and I thought I'd read that one, and then I also found some other articles from different websites to offer a different perspective on the topic. So it wasn't all just science related, but I still feel it's all connected, and it's interesting to see it from different points of view. So the article that I came across is called "What is Thought and How Does Thinking Manifest in the Brain?" It seems a little bit like a stoner topic, if you know what I mean. So it says, we can describe different kinds of thought and how they arise to some extent, but the relationship between neural activity and the nature of what we are thinking isn't well understood. We're all at it all the time, yet thinking, or how we should think about thought, is surprisingly hard to pin down. When I did a vox pop, for instance, a couple of friends described thoughts as wispy things. Another saw them as sparklers, fizzing with chaotic flashes, but containing a central light source that is controllable. All of which is decidedly unscientific. But then even the experts aren't so sure about what thoughts are, and what we can surmise from the latest neuroimaging studies suggests we may never truly pin down how they manifest in the brain. The short answer is that no one really knows what thought is, says Tim Bain, a philosopher at Monash University in Australia, and author of Thought, a very short introduction. Even so, it is useful to consider two aspects of thought, he says, their content and their nature. Kalina Christoph's definition does exactly that. Thought is a mental state, or series of mental states that has some kind of content to it, with some personal attitudes towards the content, like an attitude of remembering or believing or imagining, says Christoph, who runs the Cognitive Neuroscience of Thought Laboratory at the University of British Columbia in Canada. First, let's consider content. Thinking isn't the same as perceiving or sensing, all involved holding something before one's mind, so to speak. But thoughts are distinct in that they are independent of any stimulus produced by the thing being thought about. In terms of how they arise, Christoph identifies three streams that feed into our consciousness to instigate thoughts. Exteroceptive, from the outside world; interoceptive, from your organs and internal physiological environment; and conceptive, a term she uses to describe input that wells up from the subconscious in the form of spontaneous thought, including mind-wandering or daydreaming, as opposed to intentional thoughts such as reasoning and problem-solving. Within content there is form. There are 5 main kinds of thought, according to Russell Herbert at the University of Nevada in Las Vegas, who invented thought sampling, in which volunteers record their current inner experience when prompted randomly by a beeper. This process reveals that a thought can be verbal, visual, emotional, founded in bodily sensations, or unsymbolized, none of the above yet still distinct, or a mixture of these. There's enormous variation between individuals in terms of how they think, says Hilbert, even if many of us fail to recognize this. As for the nature of a thought, or what thoughts look like in the brain, Christoph uses functional magnetic resonance imaging to explore this. For sure there are neural correlates, she says. Some of the brain activity simply reflects the kind of thought being had. For example, a visual thought will show activation in the visual cortex. More surprising is what happens prior to spontaneous thought. About 3 seconds beforehand, there is activity in parts of the default mode network, which generally fires up when your brain is idling, and also in brain regions associated with memory. The latter have unusually diverse connections, which might help explain why spontaneous thoughts are so eclectic and arbitrary. Neuroimaging can give us a general idea of what someone is thinking then, but Christoph doesn't believe it will ever accurately interpret the subjective experience of thinking and thus make it possible to read people's minds, something that has been touted as a goal for the brain-computer interfaces being pursued by Elon Musk's Neuralink, among other companies. The mind emerges out of a physical substrate, the brain, and the relationship of emergence is not deterministic, she says. So this next article I have is from the Psychology Today website, and even though it's from the perspective of psychology, it does have a good explanation for the physical processes that go on in the brain when you're thinking about things. It actually goes into a lot more detail than the first article. And then the next article goes a bit more into the cognition side of things. What actually is a thought, and how is information physical? Google the word thought, and you will find this uninformative circular definition. An idea or opinion produced by thinking or occurring suddenly in the mind. The Merriam-Webster dictionary defines think in a similarly unhelpful way, to form or have in the mind. But what actually is a thought? A thought is a representation of something. A representation is a likeness, a thing that depicts another thing by having characteristics that correspond to that other thing. For example, a picture, image, imprint, or mold of an object is a representation of that object. A map is another example of a representation. The mind is a kind of map. The brain and its functional product, the mind, evolved as a map of the body's relation to its external environment. Fundamentally, our thoughts are maps representing and corresponding to things that our brains have either perceived with our senses, felt with our emotions, or formed as an action plan, e.g. forming an image of reaching for a ripe fruit on a tree branch. All of these are electrochemically mediated processes. Thoughts may be fleeting, or they may later be consolidated as memories. Memory too is a physical process, encoded by structural molecular changes in neuronal connections. Let's consider are transduced by the sense organs into neural signals. Let's consider how sensory perceptions are transduced by the sense organs into neural signals. Imagine hearing a clap of thunder that surprises and frightens you. The sound of the thunderclap is transformed from a specific pattern of sound waves in the air to a corresponding pattern of vibrations transmitted through your eardrum and the small bones in your middle ear to your cochlea, to a corresponding pattern of electrochemical impulses along the auditory nerve, to corresponding signals and neurons in the auditory cortex and association cortex. That's a pretty detailed description, isn't it? It also activates fear circuitry relayed via the amygdala, and perhaps also visual circuitry that records what you saw at that moment. Signals are transmitted between neurons by chemical neurotransmitters. The entire widely distributed network activated throughout the cerebral cortex by this stimulus is the experience at that moment. Since this was such a strong stimulus, a flashbulb memory moment, the pattern of connections in this particular network is then made permanently retrievable. This happens by changes in membrane proteins at the connections between all the participating neurons that fired together in response to that stimulus. Neurons that fire together wire together. Hebb's law. This constitutes the memory. The same approximate network can be reactivated in the future by a reminder, some association cue. The pattern of connections is a representation, a map, corresponding to the pattern of information that you perceived. It is likely also interwoven with representations of other feelings or memories that you associate with that experience, adding layers of meaning to the experience. Modern information theory has taught us that information is a physical entity. Rolf Landauer, an IBM physicist, stated the case. Information is not an abstract entity, but exists only through a physical representation, thus tying it to all the restrictions and possibilities of our real physical universe. Information is inevitably inscribed in a physical medium. Elsewhere, Landauer explained further, information is not a disembodied abstract entity. It is always tied to a physical representation. It is represented by engraving on a stone tablet, a spin, a charge of elementary particles such as electrons, a hole in a punched card, a mark on a paper, or some other equivalent. So too, no thought can occur without its neural substrate. Information is the pattern of organization of matter or energy, the way things are arranged in relation to each other. Consider computer code. Differences in voltage in the computer's circuitry, conventionally represented by ones and zeros, represent different alphabet letters when associated with each other in particular patterns. The letter A is represented by 0100000001. There's nothing inherently meaningful contained in a particular voltage in an isolated part of an electrical circuit. It's from the association or pattern that information emerges. Likewise, there's nothing inherently meaningful in the arbitrary symbols that comprise the letters of an alphabet or in the sounds of the individual words of a language. They assume meaning only in relation to each other and in their pairing or association with real things in the world. Just like the letter A encoded in a computer circuit, your memory of your grandmother is not contained in one neuron, a grandmother neuron, as opposed to, say, a President of the United States neuron. There is a vast network of often distant neurons that, in their connections with each other, collectively represent your grandmother memory. One particular neuron might perhaps encode a tiny memory fragment of your grandmother, let's say just one visual aspect of one particular facial contour. That is to say, that particular neuron will fire electrochemically when paired with visual input matching that contour. Nor is that one neuron dedicated solely to holding that piece of your grandmother memory. The same neuron probably participates in a great many other memories by virtue of its membership in a host of different connections with other arrays of neurons. Furthermore, different aspects of each memory are associated with a multitude of other memories. Aspects of your grandmother memory might be associated with your memory of a particular kind of apple pie. Thoughts of a more abstract nature are just higher level representations. They are built from hierarchies or ladders of representations, i.e. representations of representations. Abstract thoughts are in essence still fundamentally just maps corresponding to the external environment and the individual's position in it. A map is an analogue of the environment it's depicting. It corresponds to it. An analogue is something that is similar to or comparable to something else, either in general or in some specific detail. Maps can be regarded as a form of analogy making. A is to B as X is to Y. Cognitive scientist Douglas Hofstadter and psychologist Emmanuel Sander suggest that all thoughts are built from analogy making. They propose that categorization through analogy making is the driving force behind all thought. Our brains detect similarities or correspondences between newly and previously encountered situations, enabling the application of previously learned information to the new situation. The very essence of an analogy is that it maps a mental structure onto another mental structure. Language is replete with examples of the ways in which thought is built from analogy making. Our words for things that don't exist out there in nature are built from words that represent concrete things that we can perceive with our senses. Here is a sampling of some of the simpler analogies, metaphors from Hofstadter and Sanders' elaborate collection. The legs of a table, the spine of a book, the tongue spoken by the islanders, the window of opportunity for doing something, the field one studies, a marginal idea, salaries that fall within a certain bracket. Similarly, our 5 major senses are recruited by our language to describe abstract phenomena in familiar physical terms. For example, one can be touched by a kind gesture, struck by a beautiful scene, or hurt by a jabbing remark. Or one can taste the joy of victory, find a movie to be tasteless, be in a sour mood, or make a bitter remark. Happiness and unhappiness are represented in vertical space, to raise someone's morale, to plunge into despair, to be very down. Abstract notions are often conveyed through comparisons to familiar human activities. Her experiment gave birth to a new theory. The facts speak for themselves. A religion dictates certain behaviors. His fatigue caught up with him. Elsewhere, Hofstadter explored the question of how, through self-reference and formal rules, systems can acquire meaning despite being made of meaningless elements, and how the psychological self emerges from abstract feedback loops or self-referent symbolic representations, recursively reflecting on itself in a reverberating circuit, a cybernetic loop. Quite a dizzying concept. The neuroscientist Antonio Damasio proposed a model for how the self emerges in gradations, in organisms of increasing evolutionary complexity. According to this model, a simple organism develops a rudimentary form of self-awareness by forming a map of its body and its position in the physical space it occupies. Damasio calls the most basic representation of self the proto-self, a non-conscious state that many species may have. It's a very basic level of awareness comprised of neural patterns representing or mapping the body's physical structure. Since thoughts are physical and have spatial dimensions, each thought being represented by complex connections between large arrays of neurons, you might wonder if it's possible to read a person's thoughts from their brain's patterns of neuronal activity. In fact, scientists have already been onto that project for several years. The brain requires an inordinate amount of energy to do its work, utilizing 20% of the body's energy consumption at rest, despite accounting for only 2% of the body's weight. The brain's rate of caloric burning increases when engaged in cognitively demanding tasks. Energy and mass are interchangeable, E equals mc squared. Since thoughts are energy signals, the ions and molecules encoding the energetic signal have mass too. But can we actually calculate the weight of a single thought? Certainly it would be an infinitesimally tiny number, but not zero. In summary, information is physical and relational, and we are networks of information. Thoughts are not ethereal. They're representations of matter and are encoded in matter. They have shape and weight. Abstract ideas are analogically built from more concrete sensory representations. The sense of self is built from self-representations. Thoughts are forms of information, and all information is physical and relational. It feels like something to have a thought and to be a self because we are that information, recursively reflecting on itself in an infinite regress. That's a very interesting way to put it, isn't it? Because we are that information. It's still not really getting to the depth, maybe not depth, but we all, as thinking creatures, we all know that there's more to it than that it's more than just this physical firing of things in the brain. Just the idea of how this fleshy, squishy, fatty tissue in my head and your head can make these visual things that we can perceive and see, but we're not really seeing it in front of us, we're just seeing it up here. And what about thoughts that seemingly come out of nowhere, that might appear in our head and we think, like, I don't think that at all, that's horrible, or it's just out of the realm of your beliefs and seems just like this bizarre concept when you think about it. So the next article goes into a little more cognition part of thinking, and I like this one because even though it's another psychologist who wrote this article, the concepts that he talks about open the door to more spiritual ideas and concepts, and that really resonates with me because I've done a few sessions in therapy, like probably a lot of people have. I found it was like I needed more, and I think the component that was missing for me was the spiritual aspect of things, some deeper meaning, and that's what the missing piece was for me. And since I've incorporated that into my life, I do feel a lot more peaceful now than I used to, for the most part anyway. So this next article is called "What is Thinking?" What if all written knowledge in the world would disappear? What if you were the only one to know about this and you had the opportunity to save 5 books from vanishing? Which ones would you choose? Why these? What would you do with them? As you read these questions, your mind is probably working hard, even if your first reaction is disbelief, like this could never happen. It likely still elicited a response from your mind. We all engage in thinking daily, and it's a constant presence in our lives. It encompasses a variety of activities such as rumination, analysis, fantasy, problem solving, and storytelling, and we have little to no control over it, although some may argue otherwise. However, this article will not focus on the content of our thoughts, but rather on the nature of thinking itself. Interestingly, there's no universally accepted definition of thinking. It's a complex phenomenon that involves cognitive, emotional, and sensory processes, and can be approached from various perspectives, such as neuroscience, psychology, philosophy, and even software engineering. Each of these fields has its experts and opinions on the matter. In this article, we'll first have a look at the objective nature of thinking, biology, then venture further into the subjective nature of thinking, psychology. On my own bias, since I am a psychologist, my mind has been mostly habituated with thoughts from these schools. I often describe thinking as mental habits, processes that try to become automated through continuous repetition. More on that later. Thinking is an intricate process that has long captivated our curiosity. At its core, thinking is a product of the mind, a repository of thoughts accumulated over a lifetime. Yet the mind finds its physical residence within the brain, one of the body's remarkable organs, akin to the heart, liver, or lungs. There's much to be said about the interplay between these organs, but neuroscience looks at the brain mostly in isolation, and is one of the most dominant influences on the way we think about intelligence. The brain's infrastructure is composed of neurons, specialized cells that conduct electrical impulses and communicate chemically with their neighbors. It's through these intricate neuronal networks that the magic of thinking unfolds. Here are some fascinating insights from the realm of neuroscience that will be relevant to understand the experience of thinking. Efficiency through experience. Neuronal networks frequently used become remarkably efficient. This optimization happens through a process myelinization, where fatty insulation wraps around these neurons, dramatically increasing the speed of communication. These well-traveled neural pathways resemble mental highways, streamlining our thoughts, even if they don't follow the most direct route. The rewiring potential. Neuroplasticity, the brain's ability to rewire itself, is a revelation. It implies that our brains aren't fixed entities, but malleable structures. Negative patterns can be unlearned, and positive ones can be cultivated through deliberate practice and conscious effort. This offers hope for those seeking to change entrenched thought patterns. Emergence and complexity. From the simplicity of individual neurons emerges the complexity of brain structures. These structures give rise to our personalities, desires, and goal-directed behaviors. The remarkable aspect is that an individual neuron, minuscule on its own, contributes to the grand tapestry of our experience. From a deterministic perspective, the brain operates like a meticulously set domino lane. Researchers have uncovered studies suggesting that brain activity can predict decisions before individuals are consciously aware of making them. This has led to the notion that free will might be an illusion, as every biological process could theoretically be foreseen with all variables being known. That's very interesting. But within this deterministic framework, a fascinating concept emerges: free won't. While we may lack control over our automatic, unconscious patterns, we retain the power to choose not to act according to them. This conscious intervention may pave the way for a deliberate rewiring of thought patterns and behaviors. It's important to acknowledge the intricacies that this simplified view doesn't capture. The brain's complexity extends beyond neurons and myelinization. It involves neurotransmitters governing mood and attention, and it operates at various frequencies of communication. I've chosen to highlight these points because they are well understood and are helpful mechanisms to know when trying to look at the subjective nature of thinking. In a nutshell, individual neurons can emerge to larger, complex networks. Neuronal networks become efficient through repetition and even though accompanied by resistance. Even these ingrained highways can be changed or rewired. Embodied cognition is a contemporary framework in psychology and cognitive science that asserts cognitive processes are profoundly influenced by the body and its interactions with the environment. This perspective challenges the traditional belief that cognition is exclusively a product of the brain, instead emphasizing the role of the body in shaping our thoughts and perceptions. It does not oppose the idea that the brain is involved in thinking, but rather asserts that it co-evolved with the body, making it deeply influenced by bodily experiences. In my experience, this framework offers a highly practical and effective approach to engaging with cognition and its interplay with emotions. For instance, when you are anxious, you may experience a racing heart, muscle tension, shallow breathing, and other physical sensations. Simultaneously, your thoughts will significantly differ from those in a relaxed state. Becoming aware of the array of bodily sensations accompanying the experience of anxiety can be tremendously helpful in refraining from engaging in thoughts and behaviors associated with anxiety. From the lens of psychology, it's not the underlying mechanisms behind what we think constitutes thinking, but the underlying experiences and functions of thinking. While there are different schools of thought too, most would agree that thinking is an active process through which individuals construct knowledge by interacting with their environment. Jean Piaget differentiated between two different processes, assimilation and accommodation. While assimilation involves the incorporation of new experiences, accommodation involves modifying existing schemas to fit a new experience. This translates into first, thinking as a tool of pattern recognition, learning, problem solving, and idea generation, and second, as a tool to make meaning and tell stories, mostly about our life. Second, as a tool to make meaning and tell stories, mostly about our own life to make it seem coherent. This part of the article I find interesting because it relates to the next article that I'll read. It's taken from an Eckhart Tolle video clip that I took the transcription from that. And there's a comment that the person asking him a question makes at the end that describes thinking as a tool to help you understand any subconscious feelings you might be having that you're holding on to, and the thoughts that arise, even if they seemingly come out of nowhere, are a good indicator of that. When you can observe your thoughts for what they are rather than becoming overtaken by them, possessed by them, they can be really helpful. Anyway, moving on. Our minds are fantastic at recognizing patterns and then making the desirable patterns more efficient, faster, easier, and unconscious, just like habits. From an energy perspective, habits are incredibly resource-efficient ways to solve an evolutionary problem. Like habitual scrolling through our phone to solve the problem of getting a reward for new information. It's more resource efficient to not have to put thought into every action that involves pulling out our phones, unlocking the screen, opening social media, and so forth. Since emotions seem to be a huge driver for neuronal networking, these habits are especially easy to build if an undesirable feeling can temporarily be replaced by something lighter. In the same way mental habits can be born, Stories we keep telling ourselves become internalized. Thoughts about things we like or dislike become habitual, and ways in which we approach problems in life or at work become repetitive. We fall into the same pattern over and over again and lack creativity, thinking outside of the norm. This also implies that thinking is not strictly rational, as we would like to believe, but more of a belief than we would like to think. Thinking is believing because we build mental habits upon already existing structures we have believed to be true in the past. Interestingly, we are mostly unaware of this. We do not know what the alternative would hold. Often we are even afraid to think about it because it would interfere with our existing mental models. And on top of that, it requires effort to think outside of our ingrained patterns. One thing that the mind seems to be very good at is the solving of problems. Think of the question at the beginning of this article. Face the mind with a question and it will inevitably try to find an answer to that question. It will likely do so by drawing on past experiences. What books have I read that would be valuable for the entire world? It might also ask further questions to stimulate new thoughts. What parts of society would be most and least affected by the absence of written language? Who would suffer? Who would be better off? In our internal monologue, the questions are posed from our mind itself, though. It does not seem ideal if the party posing the question is also the one to answer it. Some would call this a conflict of interest. This can be one reason why we can get stuck in thinking, and why coaching or generally talking to other people can be valuable. They might ask questions our mind has never thought of before and stimulate it to generate new outputs, some of which might be useful enough to become assimilated and increase the quality of our lives. It doesn't change anything about the fact that our minds can be incredible at solving problems if we just let it openly generate ideas without judgment, which are often a set of thoughts that constitute a belief. Most of these ideas will likely be useless, but some might be game-changing. It's interesting to note that there's one thing that AI cannot mimic, at least not yet. Artificial intelligence is great at logical thinking with higher speed and fewer mistakes, but it lacks the ability for inefficient thinking. This type of thinking is what can lead to new insights. Throughout history, innovative ideas have played a major role in advancing society, even when they appeared unproductive or inefficient at first. Light bulbs were frowned upon at first for being an inefficient and expensive way to produce light. Just like we can observe the phenomenon of emergence in the brain, from neurons to networks to brain structures, we can observe the concept of emergence in the mind. We can go from a single thought to constructs of thoughts to entire personalities to multiple personalities. Each level adds a new layer of complexity to the human experience. When I say multiple personalities, I'm not talking about multiple personality disorder or other mental illnesses, but the mere fact that we as humans often have contradictory opinions in our minds. We may have a part that wants to be independent, show its work, influence others, and be successful, but at the same time we have a part that wants to be secure, held in the warm embrace of dependency, and hide from the world. Each of these parts can have its own thoughts and feelings, even different voices and postures without contradicting the larger nature of the self. As we construct our reality by interacting with the environment, we build up certain reactions, thoughts, behaviors, and feelings that are congruent with the current environment. But environments change. As we grow up, we take on different roles. The way we communicate with others or ourselves can drastically change depending on the environment. It would be awkward to have the same construct of thought online, during work, visiting our parents, or talking to a child. When it comes to personalities, many of us have an inner narrator that that we've become acquainted with. This voice is always there, narrating our experiences to us in the form of an inner monologue. It's like we're telling a friend about everything we've done today or in the past. Most psychologists would consider telling our own story as a means to bring coherence to our lives and add more internal consistency. By doing this, we prevent ourselves from being victimized by the randomness of the world and instead place ourselves at the center of it. I have made this decision and I am in control. Let's assume we had an upcoming project that involved public speaking and got cancelled. Our narrator might sound something like this. I've always been bad with speaking in front of people. I'm glad that project got cancelled. It could have been a disaster. And now I have more time to catch up with some friends. Now let's assume that the project didn't get cancelled. Our voice might sound something like this. Public speaking has always been so uncomfortable for me, but the reward I got was always greater than the struggle. This is going to be an amazing opportunity to grow. I can't wait to tell my friends about this. In crafting stories about our lives, the narrator tends to tailor them to align with our current beliefs. This can be beneficial as it allows us to imbue meaning into our decisions, especially when we're in good mental health. Given that many of our choices lack clear-cut right or wrong answers, such as whether to switch jobs, we may subconsciously or consciously modify the story we tell ourselves to justify our decision as correct. This example is an optimistic narrator with a growth-oriented mindset. However, these stories sometimes end up being considered as chatter or lies we tell ourselves, as John Frederickson puts it, which don't always benefit us in the same way. Often enough, these mental habits can be dysfunctional, degrade the quality of life, and be a hindrance to our higher selves. One way to do so is by leaving the stories we keep telling ourselves unchecked. Although these stories may seem true, it's often because we repeat them to ourselves. However, they may not be based in reality. We may portray ourselves as independent and hardworking, but fail to acknowledge the dependencies we've created by neglecting important responsibilities we've been putting off for a while, such as our relationships or health. We avoid acknowledging these parts because they don't fit the narrative we want to present, so we ignore them and keep repeating the stories we want to hear. Continuous repetition leads to automation, which means these mental habits become unconscious and effortless. We create shadows by shining only partial light on a fake story and begin to project them outwards. This can result in a world full of individuals who appear lazy and dependent on others. This is commonly known as the story gap. It measures the distance between the story we tell ourselves and the reality we experience. This gap is strongly linked to our level of life satisfaction. When the gap is wider, we tend to suffer more. We become haunted by our insecurities and are triggered by anything that doesn't align with our ideal version of reality. On the other hand, when the gap is smaller, we experience inner peace and are less affected by external events. This results in a happier state of being. Another way when thinking goes wrong is manifested in chatter. Continuous rumination, thought loops stuck in the past, or worry, thought loops stuck in the future, stuck in our heads. Ethan Kross described this chatter as a loss of perspective, a narrowed zooming in that makes us lose the bigger picture. One common reason for getting trapped in negative thought patterns is misusing our problem-solving abilities. As we've previously discussed, our minds generate answers when posed with a question, which can be helpful. However, it can also lead to negative thinking. For example, if we ask ourselves, "Why am I unhappy?" our minds will try to find reasons and justifications for our unhappiness. This can create a negative story in our minds that reinforces our unhappiness. However, asking about the why behind the habits we value can be beneficial. For instance, asking yourself, "Why do I want to exercise?" can reinforce the idea that exercise is beneficial and help build a habit of regular exercise. A much bigger contributor to chatter, however, is the distance between I and thought. Simple example: I'm miserable, I'm depressed and unhappy, I cannot get my life right. Or I'm having thoughts that keep telling me how unhappy I am and how little I can do about it. Both are telling the same story, just from a different perspective. The first story is told from the perspective of thinking, and the second from the perspective of the one who experiences thinking. While neuroscience offers insights into the physical processes, and psychology unveils the intricate narratives, both perspectives fall short of capturing the entirety of this phenomenon. That's what I was trying to say before, but didn't really express it articulately. And lastly, to follow on from that article, I wanted to recite a video that Eckhart Tolle has on his YouTube channel, where he attempts to answer where thoughts come from. So the woman asks the question because she has thoughts that she recognizes as not her own, or possibly patterns that have existed for years and years, like jealousy or competitiveness or being threatened and fear. These kind of things that keep us up at night. Where do they come from? Eckhart answers that the Buddha was asked a similar question, and he gave this parable. Someone shot you with an arrow. You've got an arrow stuck in your body, and before you remove it, you're trying to find out why and where it came from. What he was saying is our main concern should be to remove the arrow, instead of trying to find out where it all started. How did it start? Where did it all originate? The arrow stands for suffering, any form of suffering that is self-generated through the mind. There is such a thing as a collective mind. So many thoughts are not your thoughts really. They arise in the collective mind. They're energy fields or energetic entities that you could almost think of as little bubbles floating around, which is not literally true, but say there are these thought forms floating around, and if it discovers any resonance with anything inside you, for example any form of negativity, just a slight irritation of what someone said today, this even heavier thought form of negativity will attach itself to you, and the irritation has become something bigger. So you connect with the universal mind and it moves through you. When we deal with our so-called own minds, which is far more than our own mind, whatever awareness arises in you is not just your benefit. It has an impact on the totality of the collective mind. It's not just a personal thing, in the same way that any thinking that takes possession of your mind is not really personal. It pretends to be personal, but it's the human collective mind. In the same way, any emotion generated by that, it looks like your emotion, but it's either anger or sadness or jealousy, which is the same in everybody when it arises. It attaches itself to slightly different stories in the mind of why I'm angry, but anger is anger. It's not yours. You pick it up and then it gets hold of you, and many humans live with a mind that has taken possession of them. It pretends to be them, and they're stuck with it without even knowing it. If they knew it, it would be the beginning of freedom. But if you tell them they are, then they get angry. They don't, but their mind does, because it feels threatened. You can see how collective thought forms take possession of an entire country, like Soviet communism in Russia, Maoism in China. Millions of people are thinking the same thing. And even in our society, it's not necessarily one monolithic thought form such as that, but there are different thought forms. Through the media, they can perpetuate it, and without knowing it, our most basic assumptions, how we interpret the universe and the world around us, are thought forms that come out of the collective and take possession of us. And that's all fine in itself if there is an awareness. But if thought is all there is, it becomes destructive and insane without awareness. And the next question you have would probably be why? But then that goes back to the arrow parable. I've always liked that idea of thoughts being little bubbles going through the air and then they attach themselves to you. I think of that with creativity at times. Like you'll hear an artist explain, they often feel like they were just channeling something. They weren't thinking consciously about anything. That also gets into the idea of intuition and all these different things. So yeah, it's a very complex and interesting thing. But when I was looking up these things, I did find the Alan Watts website. It was a transcript called Mind Over Mind, and I started reading it just to see if I could add anything to this video. It's just a whole nother perspective on it. The very food for thought, Alan Watts type of material. And I thought maybe I would read that for a video as well. One day, maybe. Next time, maybe in a few weeks, I'm not sure. So, I might end this video now, guys. Thank you for tuning in as usual. Super stoked that the last video did well. So welcome to all the new viewers, and shout out to all the day ones as well for sticking by me and supporting me this far. Yeah, more videos to come, and I will see you next time. Bye. Hey you guys, welcome back. Got another science type of video for you today from the New Science website, but I did rewrite it through ChatGPT just in the interest of copyright. So the facts and general idea of the articles is still the same. It's just paraphrased. I've also got my dog in the background here. He's okay right now, but sometimes when he falls asleep, he starts to breathe kind of loudly. So we'll see how long he can sit there for. I might need to move him. So this collection of articles was in the New Scientist website. It was called We've Seen the Future and It Will Blow Your Mind. And it says, New Scientist is 60 years old this week. And what better way to celebrate a landmark birthday than to wax lyrical about another time? But we're not going to hark back to the past. We're going to gaze another 60 years forward. What is the world going to be like in 2076? And there's quite a few articles here. Some of them are about energy and electricity, population, nuclear war, science and technology, settling on Mars, genetically engineered people. So it's all speculative, really. When I looked briefly through, I could see that a lot of the articles seem to be written in 2016, so about 8 years ago. This is what some of the experts thought. So much has changed in 8 years already. I wonder if they could have predicted that. So I hope you guys sit back and relax, get comfortable, and we will read these articles now. So the first one I have for you is called The World in 2076, artificial starlight has made energy free. We already rely on nuclear fusion, but the reactor is 150 million kilometers away, our sun. We haven't figured out an efficient way to harness its power directly, so we burn its stored energy in the form of coal, oil, and gas, gradually heating our planet like a frog in boiling water. Creating a sun-like fusion reactor on Earth could help solve this issue, though it's a massive challenge. Research into nuclear fusion began over 60 years ago, and the leading design, the tokamak, has been around for half a century. Tokamaks confine heavy hydrogen isotopes within a donut-shaped magnetic field. Heating and compressing the plasma to fuse deuterium and tritium, releasing energy. After testing a series of progressively larger tokamaks, fusion researchers decided a decade ago to construct a massive one in France, named ITER. If all goes according to plan, which is unlikely, ITER will generate 500 megawatts of energy for a few hundred seconds by 2035, making it the first fusion reactor to produce more energy than it consumes. However, two significant challenges will remain, according to Mickey Wade, Vice President of General Atomics and Director of the US-based DIIID fusion program. One is developing materials that can endure prolonged plasma exposure, and the other is maintaining the strong magnetic fields needed to confine the plasma. Overcoming these challenges would be a monumental breakthrough. Fusion could largely eliminate our dependence on fossil fuels, providing clean and extremely cheap energy in nearly unlimited quantities. But would it? While fusion power is cleaner than fossil fuels, it isn't entirely carbon neutral. Although the reactors don't emit carbon directly, the processes involved in construction, fuel production, and waste management have their own carbon footprints. Fusion also produces radioactive waste, though it decays in decades rather than centuries or millennia. Additionally, fusion power won't be too cheap to meter. The reactors are incredibly expensive to build, with ITER's cost exceeding 20 billion euros. Investors will need to recoup their expenditures, but once operational, the running costs will be low. The oceans hold enough deuterium to fuel fusion reactors for tens of thousands of years. Tritium, while rare in nature, can be produced from lithium, which is abundant. Although fusion power could theoretically support the entire world, it's unlikely in practice. Fusion plants would likely be used primarily for baseload power, with energy storage technologies like ultracapacitors charged by solar and wind, meeting peak demand. We'll also need new methods to power airplanes and other technologies that can't rely directly on grid power. Fusion might still be an elusive future technology 60 years from now. Solar and wind may not fulfill all our energy needs. If that happens, we might have to rely on nuclear fission, with its associated risks of accidents, long-lived waste, and proliferation of nuclear weapons. Advances in superconductivity and geoengineering could potentially help, but ultimately we need a substantial amount of homemade sunshine by 2076. And that's the end of the first article. The next one, also related to energy, is called The World in 2076, Goodbye Electricity, Hello Superconductivity. 30 years can seem like an eternity when waiting for the next groundbreaking discovery. For half of the new scientists' existence, a dedicated group of researchers has believed that a world-altering breakthrough is imminent. Yanming Ma of Jilin University in Changchun, China, says such a discovery would bring revolutionary change for our normal life. The breakthrough in question, a superconductor that functions at room temperature and normal pressure. While this might not sound exciting at first, the implications are monumental. Superconductors are materials that conduct electricity without any resistance. This phenomenon was first observed by Dutch physicist Heike Kamerlingh-Onnes in 1911, when he found that mercury's resistance dropped to zero at 4.2 degrees above absolute zero. Other materials were later discovered to be superconducting at slightly higher temperatures, but the need for extreme cooling limited their practical applications. That changed in 1986 with the discovery of high-temperature superconductors, which stop resisting below approximately negative 170 degrees Celsius. Although high temperature is a relative term here, this discovery made the idea of room temperature superconductors seem more plausible. However, the next major leap forward has not yet occurred. According to Paul Atfield of the University of Edinburgh in the UK, we have not surpassed the advancements made 30 years ago. New materials have been found to superconduct at somewhat higher temperatures, but only under extremely high pressures. For now, superconductors remain impractical for the transformative applications needed to change the world, such as transportation and power transmission. Superconductors can repel magnetic fields, allowing magnets to levitate above them. This property makes them ideal for highly efficient, frictionless maglev trains that hover above tracks. The absence of energy loss is also crucial for power supply. Currently, electricity sent from power stations to consumers encounters resistance in wires, resulting in significant energy loss. With superconducting cables, there would be no such loss, allowing batteries using these materials to stay charged indefinitely. These technologies could resolve many global energy issues without relying on another potential energy revolution, nuclear fusion. My dog had very minor surgery today, so he's a bit whiny and sad. Keeps letting out these little whimpers. Mikhail Erametz of the Max Planck Institute for Chemistry in Mainz, Germany, believes a world powered by superconductivity is within reach. He states there are no theoretical barriers to achieving room temperature superconductivity. In August, a team led by Ivan Bosovic of the Brookhaven National Laboratory in Upton, New York, published a groundbreaking paper in Nature that could point the way forward. It suggests a strategy change in our quest. Bosovic says, "I'm optimistic." Can you hear my dog breathing. I can definitely hear it. I hope I don't get to editing this and I realize it's totally distracting. So moving on from the energy speculation, the next article is called Stanislav Lem, the man with the future inside him. From the 1950s onwards, science fiction writer Stanislav Lem began creating visionary works that anticipated our present and extended far into the future. His foresight remains unmatched. In William Burroughs' 1961 novel, The Soft Machine, a scene describes people compulsively approving and repeating slogans, hinting at a form of social media. Such predictions, while interesting, are often lucky guesses. For instance, Robert Heinlein's 1948 story, Space Cadet, features microwave food. But does this really matter? Futurology involves more than guesswork, and not all predictions are shallow. Ray Bradbury, writing in the 1950s, envisioned earbud headphones and elevator music, foreseeing the eerie reality of today's media-heavy shopping malls. However, even Bradbury's predictions were often exaggerations of his own time, imagining more TV, more suburbia, and cars without roads. Writers like Frederick Pohl and Arthur C. Clarke depicted futures that were extensions of their contemporary decades. Stanislav Lem, the Polish satirist, essayist, and science fiction writer, dismissed such predictions. Meaningful prediction, he argued, is not about serving up the present with startling improvements or revelations instead of the future. Lem sought to capture the entire human adventure in all its complexity and grandeur, creating new chapters in our story rather than simplistic happy endings. Remarkably, Lem's foresight was extraordinary. Nearly a year before the Cuban Missile Crisis, his 1961 book, Memoirs Found in a Bathtub, captured the irrationality of Cold War policies. While others imagined a future of tightly controlled information, Lem envisioned the internet and the flood of misinformation it would bring, eroding civic freedoms. 2 decades before virtual reality became a term, Lem wrote about its educational and cultural impacts, coining the term phantomatics. His 1964 book, Summer Technology, addressed ethical questions in genetic engineering long before they became mainstream. Lem also imagined nanotechnology, including space elevator cables made of spider silk and the catastrophic grey goo scenario, well before these concepts entered public discourse. He even anticipated the technological singularity, the idea of artificial superintelligence sparking rapid technological growth, before Gordon Moore formulated his famous law on the exponential growth of computing power. Not all his predictions were serious. Lem coined the phrase theory of everything to mock the concept. Born on September 12, 1921, in Poland, Lem developed his critical perspective early, shaped by near-death experiences during World War II. His rational outlook viewed human use of reason as a way to navigate a world dominated by chance. An inventive mind, he was disappointed to discover that many of his school inventions, like the differential gear, already existed. His understanding of systems began with creating a bureaucratic state complete with internal passports events during his childhood. Lem's first novel, Hospital of the Transfiguration, 1955, was rooted in the absurdity of his world. He turned to science fiction to evade Stalinist censors, becoming prolific after Poland's post-Stalinist thaw in 1956. Over the next 12 years, he published 17 books, including Solaris in 1961, his most famous work amongst English speakers. Solaris tells of a group of experts orbiting an inscrutable sentient planet struggling with its painful resurrections of their dead. The novel reflects Lem's pessimistic view on the search for extraterrestrial intelligence. He believed alien intelligences exist but are likely incomprehensible to us, possibly ignoring communication or living in simulations rather than facing the physical world. Lem argued that reason is an artifact, limited by human creation. An extraterrestrial reason could be vastly different. This theme is explored in Fiasco in 1986, where alien reason diverges significantly from our own. Lem's understanding of history was unparalleled among futurologists. He believed that violent and genocidal impulses are constant, while our destructive capabilities grow. If humanity survives its own destructive tendencies, the challenge will be managing our success. In The Chain of Chance, 1975, Lem envisions a future on the brink of complexity, where governments seem increasingly impotent, a prescient prediction about the fusion of accessible media and global terrorism. Should humanity master the universe, technology will eventually replace natural selection, enabling us to re-engineer our planet and ourselves. At the extreme of his vision, Lem imagined abandoning our current reality for a new one, yet still subject to historical contingencies. In his fictitious review of Professor Dobbs' Non-Servium, he depicted a creator who might destroy a beautiful, intelligent, artificial universe due to budget constraints, a grim reminder of our vulnerabilities. Most futurologists seek utopias, desiring an end to history and a happy ending. Lem, however, wanted to see what lay beyond, believing that history is real and continuous. He recognized that solutions create new problems and that no perfect world exists, either in the past or the future. By his death in 2006, Lem had sold nearly 40 million books in over 40 languages. He earned acclaim from futurologists, scientists, and philosophers. Lem advised realism, patience, and intelligence, reminding us that the world is vast and our journey has just begun. So the next article is a bit dark, but I promise they're not all like this. It's called The World in 2076, That Nuclear War Was a Bit of a Bummer. So it's probably dark, but I think I have always had a bit of a curiosity about nuclear war. I don't really need to know what would happen, but I've kind of wondered a little bit. So I'll just try to think of it like that. It's informational. It's just talking about what could happen. Okay. With tensions flaring once more between Moscow and Washington, along with the ongoing conflict between India and Pakistan over Casmir, and China's expanding nuclear capabilities, threat of nuclear war remains a chilling possibility. Concerns persist about Iran's nuclear ambitions, and North Korea is now a recognized nuclear power. Although the Cold War has ended, the nuclear arsenals and geopolitical hotspots remain. Could we see a nuclear conflict within the next 60 years? Currently, the world holds around 10,000 nuclear warheads, predominantly owned by Russia and the US. But what if these two superpowers refrain from launching their weapons, and instead a nuclear conflict erupts between India and Pakistan? Many outside South Asia might think such a war wouldn't impact them significantly. This assumption is gravely mistaken. India and Pakistan together have over 200 nuclear warheads, which are relatively small compared to those of the superpowers. If they deploy half of them, around 100 weapons each, with the destructive power of Little Boy, the bomb dropped on Hiroshima in 1945, the consequences would be catastrophic. The immediate aftermath in megacities like Delhi would be devastating, with millions affected by the explosions, firestorms, and radiation. But this would only be the beginning. According to simulations by Alan Robock of Rutgers University and Michael Mills at the National Center for Atmospheric Research, the resulting fires would propel about 5 million tons of black smoke into the stratosphere, where it would disperse globally. This dense smog would reduce solar radiation reaching the Earth's surface by 8%, leading to a dramatic drop in average winter temperatures by 2.5 to 6 degrees Celsius across North America, Europe, and much of Asia. These effects wouldn't be short-lived. They would peak around 5 years after the conflict and linger for over a decade. In addition to the nuclear winter, climate models predict a severe reduction in rainfall as weather systems lose energy. The collapse of the Asian monsoon would result in up to 80% less water for 2 billion people. The Amazon basin and arid regions like southwestern US and Western Australia would suffer similarly drastic reductions in rainfall. The smoke would also heat the stratosphere by about 30 degrees Celsius, triggering chemical reactions that would destroy much of the ozone layer. However, the greater threat would come from the near ice age temperatures, which could shorten the growing season in mid-latitude regions by up to 40 days. These devastating consequences would arise from a relatively small regional conflict. Stephen Starr of the University of Missouri has estimated that a nuclear war between US and Russia could inject 150 million tons of smoke into the stratosphere, blocking 70% of sunlight and cooling much of the world by 20 degrees Celsius or more. One of the greatest achievements of the past 60 years has been avoiding nuclear war. As we look to the future, we must hope this record continues. Yeah, we do. We've done pretty well so far. So I don't think there's anything more to do with war. I don't think, anyway. Next article is called "The World in 2076. The Anti-Science Backlash Has Begun." What's interesting about this one, it was written in 2016, so this is before COVID and all of that. So, okay. After the death of polymath John von Neumann in 1957, his friend and collaborator Stanislav Ulam wrote a tribute to a man who significantly advanced science and technology in the post-war era. Ulam noted that von Neumann had expressed concern about the future support for science. Human interests may shift, current scientific curiosities might fade, and entirely new preoccupations might dominate human minds in the future. Von Neumann's fears seemed overly pessimistic given the astounding scientific and technological advancements of the past 60 years. However, public attitudes can be unpredictable. Could his concerns become reality? Jack Stilgo from University College London, who studies the impact and perception of science and technology policy, voices similar concerns today. I do worry that public opinion might turn, he says, if people feel that innovation primarily benefits the wealthy, exacerbating inequality and neglecting broader social needs. Disenchantment could set in. Will society still embrace technology when robots take over jobs, or when insurance premiums skyrocket because human drivers are deemed the most hazardous? Could self-driving taxis face the same fate as automated looms attacked by Luddites in the past? In some small, discontented communities, the backlash has already started. Former mathematician Ted Kaczynski, known as the Unabomber, has published a book titled The Anti-Tech Revolution. He seems to believe that the only solution is to drastically scale back our scientific and technological pursuits, even if it means a violent regression in human lifestyles, says Steve Fuller, a sociologist at the University of Warwick in the UK. The book reads like a revolutionary manual on how to prevent science and technology from destroying the planet. Stilgo remains skeptical. Societies in affluent countries are deeply dependent on science and technology, so a complete reversal is unlikely, he asserts. Nonetheless, if public sentiment did shift against scientific progress, the consequences would be dire. Harvard University's historian of science Matthew Hirsch warns, a public mood that discourages scientific research would lead to technological and economic stagnation, resulting in technical and financial ruin. The social implications would be devastating as well. When academic institutions cease to discover new knowledge, their education deteriorates into dogma, half-truths, and untested assumptions derived from flawed texts, Hirsch explains. The possibility of a future where the public turns against science might seem distant, but it highlights the importance of ensuring that technological progress benefits all of society and addresses broader social needs. So the next article, The World in 2076, Human-Made Life Forms Walk the Earth. Life first emerged on Earth almost immediately after the planet cooled enough to support it, and since then it hasn't spontaneously arisen again over the span of 4 billion years. However, this long period of biological stasis might soon come to an end as scientists approach the groundbreaking achievement of creating life from non-living materials in the lab. Geneticists have already made significant strides by synthesizing custom genomes and inserting them into bacteria. They've also successfully altered the genetic code of bacteria to enable them to use novel, non-natural building blocks to produce proteins. These feats, though impressive, begin with pre-existing living organisms and involve modifying them. A more daring initiative aims to start with non-living chemical ingredients, sometimes using familiar nucleic acids and lipids, but at other times employing radically different structures like self-assembling metal oxides. The objective is to guide these chemicals to cross the Darwinian threshold where they can replicate themselves heritably and evolve, meeting the essential criteria for being considered alive. If scientists achieve this, the ramifications would be profound. Most fundamentally, creating synthetic life would complete the philosophical shift initiated by Darwin from a creation-centric perspective of the living world. It will demonstrate conclusively that life is nothing more than a complex chemical system, says Mark Bedeau, a philosopher of science at Reed College in Portland, Oregon. While most scientists already accept this view, synthetic life would solidify this understanding in a way that the general public could not ignore. Moreover, achieving this in the lab would suggest that the origin of life is a relatively attainable event, thus increasing the likelihood of finding life elsewhere in our solar system. A second genesis would also provide biologists with an independent comparison point to better understand the fundamentals of life. Since synthetic life would be man-made, scientists could modify it, changing its components to discover which traits are truly essential. According to Stephen Benner from the Foundation for Applied Molecular Evolution in Florida, what we consider natural life is burdened with billions of years of evolutionary history, making it challenging to discern what is essential for life itself versus what is essential for our specific form of life. Newly created life forms would offer a cleaner system for experimentalists to investigate life's fundamental requirements. The practical applications of synthetic life may be further in the future. Initially, any new life form would be so delicate that it would need constant nurturing in a lab environment. Thus, biotechnologists aiming to produce specific molecules or degrade toxic waste might find more success by modifying existing natural life forms. However, in the long term, artificial life might evolve to be robust enough to survive independently. If this happens, it would allow biotechnologists to break free from the limitations of natural life to achieve new goals. We can explore a vast array of potential benefits, says Lee Cronin at the University of Glasgow, UK. These benefits come with significant risks. A self-sustaining, independently evolving life form is inherently unpredictable and uncontrollable. Biotechnologists will need to design effective off-switches to neutralize synthetic life forms should they become pathogenic or otherwise harmful. Additionally, policymakers and ethicists must determine when and how to activate these safety mechanisms. The public may oppose such advancements, raising familiar concerns about playing God. Therefore, discussions about the implications of synthetic life need to begin promptly. This could become a pressing issue in the short time, warns Bedeau. In summary, while the creation of synthetic life presents extraordinary opportunities for scientific and technological advancement, it also necessitates careful consideration of the ethical, safety, and societal implications. The journey from non-living chemicals to new forms of life is not only a scientific endeavor, but also a profound philosophical and practical challenge. It feels like almost every day I'm hearing about the advancements with AI and non-human life with human life becoming cyborgs and things like that. Even 10 years from now, things will be really different. And this next article, even more futuristic. The world in 2076, thousands of people have settled on Mars. By 2066, Mars has become home to a pioneering community. As the sun rises over a rust-colored horizon, lighting up the hydroponic fields, the first permanent Martian settlers begin another 24-and-a-half-hour day. Elon Musk envisions this as a reality. In September of 2016, the SpaceX founder shared his ambitious, albeit still somewhat vague, plans for sending humans to Mars within the next decade or so. He even suggested that by the 2060s, 1 million people could be living on the red planet. NASA's timeline aims for the first human landing in the 2030s. Significant groundwork is necessary before settlers can establish a thriving community. This involves sending massive amounts of life support equipment, habitats, energy systems, food supplies, and technology for extracting breathable oxygen and drinkable water from Mars's atmosphere. This undertaking is monumental. The shortest journey from Earth to Mars takes about 5 months, and this window only opens every 2 years when the planets align. Optimistically, this provides around 22 optimal launch opportunities to prepare Mars for human settlement by 2060. However, recent setbacks like the failure of the ExoMars lander highlight the difficulties of landing on Mars. The planet's gravity accelerates descending crafts, while its thin atmosphere makes parachutes ineffective. The heaviest object landed so far, the 1-ton Curiosity rover, required a combination of parachutes, retro rockets, and a sky crane for a successful landing. Current technology cannot land anything heavier than Curiosity. SpaceX plans to utilize supersonic retropropulsion, essentially reversing down with booster rockets firing to slow descent, and aims to test this system soon. NASA is collaborating on this project, hoping to gain valuable insights. The journey to Mars and survival afterward present numerous hazards: high radiation levels, solar flares, abrasive dust, and temperatures plummeting to minus 125 degrees Celsius. Additionally, growing food on Mars remains an unresolved challenge. Assuming we overcome these obstacles, what then? Enthusiasts of space exploration often draw parallels to historical migrations, where humans set off for unknown and potentially dangerous new lands. However, Mars offers no resources to exploit, unlike the New World where European settlers hoped to find riches or at least land for farming. Early Martian settlers will be reliant on Earth for a long time, making self-sufficiency by 2060 seem highly optimistic. One significant contribution settlers could make is scientific research. Humans on Mars could conduct experiments much faster than robotic rovers. Moreover, research into growing food would become a top priority. We have a precedent for a remote but vital research outpost, Antarctica. While no one lives there permanently, scientists make temporary stays to to conduct unique research, Mars might follow a similar model. Another difference from historical explorations is the constant, albeit delayed, communication with Earth. Martian settlers will remain connected with those on Earth who will witness both their triumphs and setbacks. This connection could significantly influence our decision to continue exploring the solar system or retreat to Earth. If we manage to secure food, air, and a sustainable living environment on Mars, these advancements could be adapted for other planets or moons. Mars represents the first major test of our potential to become a multi-planetary species. I'm trying to think if I would go to Mars. I'd probably go to visit. Just lots of desert. Yeah, I don't know about that. Anyway, moving on. Next article. The world in 2076. Now we can easily make whatever we want. Wonder what they mean by that. Imagining a world without scarcity challenges our conventional thinking. Typically, when we envision the end of material needs, it's on a personal level, notes John Quiggin, an economist from the University of Queensland in Brisbane, Australia. But what if everyone's needs were met? Scarcity underpins our fundamental economic framework, he explains. This is the essence of capitalism, a system whose principles seem as fixed as the laws of nature. What would happen to the economy if everything were free? Who would produce goods if there was no monetary incentive? Wouldn't this be akin to communism? Contemplating a world not driven by the market is like a fish trying to understand life outside water. Jeremy Rifkin tackled this concept in his 2014 book, The Zero Marginal Cost Society. He argues that capitalism is on the brink of outliving its usefulness. It's the ultimate market triumph, he says, a shift to a society where automation drives production costs to nearly zero, rendering products essentially free. For a glimpse of this future, look at the music and publishing industries. The internet has drastically reduced the costs of creating and distributing content. While disruptive for some, Rifkin views this as a precursor to a broader shift across all sectors. Key to this transformation will be advanced fabrication devices that can produce almost anything on demand. Imagine today's 3D printers, but far more advanced, akin to comparing a modern computer to a 1960s calculator. In about 60 years, these devices could evolve into what are known as molecular assemblers. This concept, introduced by Eric Drexler in 1977, envisions nanofabrication machines capable of manipulating individual molecules with great precision and speed to create any desired object. With a press of a button, you could produce food, medicine, clothing, or bicycle parts with minimal investment and effort. Although we can't predict exactly what such a world would look like, some outlines are becoming clearer. Rifkin predicts that these fabricators will drive a sharing economy. Ownership will transform into access. Think of services like Spotify or Uber applied universally. And instead of buying, you'll print what you need. Within 2 decades, Rifkin suggests, capitalism will no longer dominate economic life. It will share the stage with a new system it helped create. by 2076, capitalism might have entirely phased out, replaced by a society where basic needs are universally met. Rifkin calls this new economic model the commons, which will redefine not just the economy, but the very environment we live in. In this new world, you'll still work, but not for money. Your employer will be a non-profit organization. Your wealth will be measured in social capital, reflecting your reputation as a contributing member of society. Contributions to open source projects or sustainable living practices will enhance your social standing. Apps tracking your contributions to the commons, whether through your work, energy conservation, or other community beneficial actions, will allow you to exchange these social credits for luxuries, like an antique chair that's distinctly not mass-produced. Even in this future commons, our humanity will persist. Okay, so the next article is called "The World in 2076. Genetically Engineered People Are Everywhere." So this article starts with a story about a CRISPR baby. I think this might be fictional because I tried to look up the name and I couldn't find anything. So it says, in April 2021, the birth of Taro Yamada in Tokyo captured global headlines. Dubbed the miracle boy by the media, Taro's birth was extraordinary because his father, due to a Y chromosome mutation, was considered completely infertile. Yet genetic tests confirmed Taro was indeed his son. This groundbreaking event was made possible through an innovative procedure at a fertility clinic. The clinic extracted stem cells from Taro's father, corrected the Y chromosome mutation using CRISPR genome editing, and derived sperm cells from the corrected stem cells. These edited sperm cells fertilized the mother's eggs, embedding the genetic correction into Taro's DNA. Thus, Taro Yamada became the first individual with an edited genome. Taro was the pioneer, but he would not be the last. While some nations tightened regulations to ban genome editing following his birth, others saw it as a justified means to help infertile parents have biologically related children. Consequently, the number of genome-edited births began to climb, first dozens, then hundreds, then thousands annually. These children looked no different from their peers because their genomes were carefully edited to be entirely normal. This is likely the onset of the germline genome editing revolution. There's considerable discussion about editing heritable DNA to eliminate genes for diseases like cystic fibrosis. However, most conditions can already be avoided by screening IVF embryos before implantation. So why would future parents choose genome editing over pre-implantation genetic diagnosis, PGD, which is safer and cheaper? PGD is limited to screening out 1 or 2 harmful mutations at a time. Genome editing, on the other hand, promises the ability to make multiple changes simultaneously. Once germline editing is used for infertility, fertility clinics will probably offer to adjust other genes at the same time. Critics will call this a slippery slope, while supporters will see it as logical, even humane progress. Since everyone has hundreds of mutations that elevate the risk of cancer, Alzheimer's, and mental disorders, why not eliminate the worst ones? In fact, if it can be done safely, it might be considered unethical not to. And why stop at eliminating harmful mutations? Beneficial gene variants could also be introduced, making people immune to HIV or less prone to obesity. By the 2030s, some countries might permit the addition of such advantageous traits. These interventions would be highly controversial. Even more contentious would be the enhancements of traits like personality, intelligence, or other valued characteristics. Currently, no single gene variant has been identified that significantly boosts IQ to the extent that factors like wealth or education do. The complexity of the brain suggests that we may never fully predict the impact of specific mutations. Therefore, introducing brain-altering mutations not naturally occurring would be an enormous risk, one that neither parents nor regulators should take. However, genome editing can indisputably reduce susceptibility to numerous diseases. As it becomes evident that genome-edited children are generally healthier than those conceived traditionally, affluent parents may choose genome editing even without pressing medical reasons. Could this create a further advantage for the wealthy, widening the gap between rich and poor? Quite possibly. However, by the time New Scientist celebrates its 120th anniversary, it's plausible that many countries will routinely and uncontroversially offer genome editing to prospective parents, considering that the long-term healthcare savings will outweigh the costs of the treatment. I had heard that they were already doing this. Was that just a conspiracy theory? But I never looked into it. And if you consider the last article that talked about everything becoming free, there wouldn't be any price for genome editing babies, while also incorporating technology, and we're just going to be superhuman, aren't we? The difference is going to feel like how we almost look at Neanderthals, and like we're going to be the new Neanderthals. Crazy. So the next article is called "The World in 2076. We Still Haven't Found Alien Life." For decades, we've been on a quest to discover if we are alone in the universe, employing increasingly advanced technology in our search. Mars rovers explore the planet's surface, and missions are in the works to investigate Saturn's moon Enceladus and Jupiter's moon Europa, both potential havens for liquid water. The James Webb Space Telescope, scheduled for launch in 2018, will allow astronomers to analyze the atmospheres of exoplanets for signs of life. Meanwhile, radio astronomers continue to listen for signals from intelligent extraterrestrial civilizations. Despite these efforts, we've found nothing. What if, by the middle of this century, we've explored all potentially habitable locations in the solar system, monitored radio waves from millions of stars, and scrutinized countless exoplanets, yet still come up empty-handed? Should we then conclude that we're truly alone? I don't think so. Those involved in the search assert that giving up is not an option. Mary Wojtek, director of NASA's astrobiology program, emphasizes that the vast number of stars and planets make it inconceivable that life hasn't arisen elsewhere. With approximately 100 billion galaxies in the known universe, each containing roughly 100 billion stars, even the most improbable events are likely to occur somewhere. If we fail to find alien life, It would prompt researchers to question their methods and assumptions rather than the existence of extraterrestrial life itself. John Willis, an astronomer at the University of Victoria in Canada, and author of a book on the search for alien life, points out that defining life is complex. Unlike the straightforward detection methods depicted in science fiction, real-life searches are more nuanced. For instance, while we look for water and oxygen on exoplanets, alien life might not rely on these molecules. Additionally, while we listen for radio signals from extraterrestrial civilizations, they might use communication methods beyond our current understanding. Even if alien life exists on a distant exoplanet, we might not detect it unless it significantly alters its planet's atmosphere. If our current searches yield no results, researchers will revisit their strategies, developing more sophisticated and sensitive techniques for future explorations. Of course, it is possible that we are alone in the universe, a solitary and highly improbable occurrence. If this is the case, scientists would need to reconsider their theories about the conditions necessary for life and what makes Earth unique. John Willis suggests that if the universe is indeed empty and we are the first life forms, we bear the significant responsibility of preserving ourselves and the planet. So I got a couple more articles for you guys. This one is The World in 2076. The theory of everything is here, we think. Let's be honest. Our current understanding of the universe is just a step towards uncovering something even more profound. History teaches us this about fundamental theories of nature. Consider Newton's universal law of gravity, which accurately described falling apples and orbiting planets for over 2 centuries until Einstein's general relativity offered a more precise understanding. Similarly, classical mechanics, which seem straightforward, become hazy with quantum uncertainty when examining subatomic particles. Quantum theory elucidates matter's behavior on a small scale, while general relativity explains the universe's large-scale dynamics. Each theory is highly accurate within its domain, but has gaps and inconsistencies, suggesting that they too are temporary placeholders for a more comprehensive theory. A theory of everything would address the areas where quantum theory and relativity fail, such as within black holes or during the universe's earliest moments. Many brilliant minds have stumbled in pursuit of this ultimate theory. Einstein spent his later years in a fruitless quest for such enlightenment. Progress has been slow since then. String theory, which proposes that fundamental particles are tiny vibrating strings, remains unproven and criticized for its lack of testable predictions. Alternative theories like loop quantum gravity have emerged but also lack definitive breakthroughs. Despite these challenges, the outlook for the next 60 years is optimistic. Mike Duff from Imperial College London, who has studied theories of everything since the late 1960s, is hopeful about the timeline. While I'm hesitant to make predictions, if pressed, I'd say it will take more than 10 years, but less than 100, he says. Carlo Rovelli from Aix-Marseille University in France, a prominent figure in loop quantum gravity, shares this optimism, believing that we will have a theory of quantum gravity within 60 years. However, the development of such a theory will mark a beginning, not an end. Theories gain acceptance over time. Predictions of general relativity, such as black holes and gravitational waves, were fully realized only decades after the theory's introduction. gravitational waves were finally confirmed just recently, a unified theory will likely operate at energies far beyond our current capabilities, meaning experimental verification might be subtle and indirect. It could come from patterns in the cosmic microwave background, radiation from the Big Bang. Immediate practical applications of such a theory are unlikely, though not impossible. Ravelli notes, I don't see technological applications of the theory right now, but nobody imagined GPS back in the 1970s when I started studying general relativity. Thus, any breakthroughs will probably come gradually, with no single eureka moment. But the unexpected is always possible. When Paul Dirac unified quantum theory and special relativity in the 1920s, he predicted a second particle alongside the electron. The discovery of the positron soon after opened the door to the world of antimatter, a realm still not fully explored. A theory of everything, possibly based on string theory, might suggest the existence of a multiverse, vastly expanding our understanding or our questions. This pursuit excites scientists like Duff, who says, most scientists are trying to become masters at the game. Theoretical physicists are still trying to understand the game. And the last article I have for you guys today is called The World in 2076. Machines outsmart us, but we're still on top. The outlook for the future seems grim from many angles. The world is besieged by environmental, economic, and political pressures. It's challenging to determine the most significant threat. Our existence itself is precarious, with dangers such as asteroid impacts, global warming, pandemics, or rogue nanomachines turning everything into grey goo. Another looming threat is artificial intelligence. In December 2014, Stephen Hawking warned the BBC that the development of full artificial intelligence could spell the end of the human race. It would take off on its own and redesign itself at an ever-increasing rate. Humans who were limited by slow biological evolution couldn't compete and would be superseded. Later, he added that AI could be either the best or worst thing to ever happen to humanity. Prominent figures like Elon Musk, Bill Gates, and Steve Wozniak have echoed similar concerns about AI's potential risk to humanity. Yet investment in AI research continues to soar, leading to remarkable advancements. In a landmark event, a Go master lost 4-1 to the AlphaGo computer in March. In numerous fields, from driving taxis to winning aerial dogfights, machines are starting to outperform humans. Hawking's apprehensions center on the concept of the technological singularity, the point when machine intelligence surpasses human intelligence, heralding a new, superior species on Earth. The notion traces back to thinkers like John von Neumann, a computing pioneer, and science fiction author Vernor Vinge. Stanislav Ulam, in a 1958 tribute to von Neumann, mentioned a singularity in human affairs prompted by accelerating technological progress. Ray Kurzweil and Nick Bostrom have popularized the idea of a technological singularity in recent times, predicting it could occur around 2045. Machines overtaking humans in intelligence is alarming because humanity's dominance stems largely from our intellectual capabilities. While many animals surpass us in physical attributes, our intelligence has enabled us to develop tools, agriculture, and technologies like steam engines and smartphones, cementing our control over the planet. The prospect of machines that think, and think better than us, threatens to displace us. Just as other animals rely on our goodwill for their survival, we might find our fate dependent on the decision of superior thinking machines. The concept of an intelligence explosion, where machines rapidly enhance their intelligence, isn't far-fetched given the exponential growth trends in computing, such as Moore's law, which predicts the doubling of transistors on integrated circuits every 2 years. Despite the advancements, several arguments suggest a technological singularity may be unlikely. The fast-thinking dog argument posits that speed alone doesn't equate to increased intelligence. Even if a dog could think faster, it wouldn't play chess because it lacks the necessary cognitive constructs. Similarly, increasing computer processing speed doesn't automatically result in smarter AI. Intelligence is more than fast computation. It involves years of experience and learning, which may not be easily replicated in silicon. The anthropocentric argument challenges the idea that human intelligence is a unique tipping point. History shows we are not as exceptional as we like to believe. Copernicus, Darwin, and the discovery of DNA have all revealed our less than special place in the universe. There's no reason to assume that human intelligence is a special threshold for rapid advancements. The diminishing returns argument suggests that improvements in intelligence may not yield constant multipliers, but face diminishing returns. Early AI advancements offered low-hanging fruit, but further progress could be harder to achieve, limiting the extent of intelligence enhancement. The limits of intelligence argument highlights the fundamental constraints of the universe. Physical laws limit speed, accuracy, and predictability, and thinking machines will also face these limits. Superhuman intelligence won't necessarily overcome these fundamental barriers. The computational complexity argument notes that many computational problems are unsolvable even with exponential improvements. The halting problem, for instance, remains unsolvable regardless of computational advancements, highlighting the inherent limitations within computing. Given these challenges, a technological singularity may never occur. However, AI could still achieve superhuman intelligence through painstaking programming. This gradual impact may delay the societal changes feared by many, but planning for AI's influence on work and warfare is crucial. Many jobs may disappear, increasing societal inequalities, and AI could revolutionize warfare, potentially destabilizing global order. Proper regulation, like banning battlefield robots, is essential to avoid dystopian outcomes. If managed correctly, AI could enhance health, wealth, and happiness. If mishandled, it could be humanity's gravest error. I feel like that article pretty much summarizes everything that I've heard recently about AI and the potential pitfalls, but also the potential for it to be very helpful. And I always hear arguments from both sides, really. But we're kind of seeing the positive aspects of it now in real time, whereas the fears about AI are more theoretical. Like there's been the occasional thing that's happened that has made people worry, but still something that's worth thinking about, definitely. So that is a speculative look into the future. What do you guys think? There were more articles that were part of this series, but do you think that covered a lot of it? guess there's a whole bunch of things we don't even know what to even expect, which is why it's exciting and scary. I feel like I could almost keep reading this, but it's probably worth ending the video here. I hope you guys liked this one. I hope it was sciencey enough. Feel free to recommend me anything else you guys would like to hear more about, or just like me to read. I'm always open to suggestions, so yeah. Thanks guys, thanks for tuning in, and I will see you next time. Bye. The deep sea is a realm of extreme conditions, mysterious creatures, and fascinating scientific phenomena. Here are 100 facts about this dark and largely unexplored part of our planet. The deep sea begins where the sunlight starts to fade, typically around 200 meters or 656 feet below the surface. Absolute darkness reigns beyond 1,000 meters, 3,280 feet, a zone known as the aphotic zone, where photosynthesis is impossible. Pressure increases by about 1 atmosphere, or roughly 14.6 psi, for every 10 meters, 33 feet, of water depth, reaching extreme levels in the deep sea. The average depth of the ocean is about 3,688 meters, which is about 12,000 feet, with the majority of the ocean's volume being deep sea. Hydrothermal vents, also known as black smokers, are found in the deep sea and can emit fluids exceeding 400 degrees Celsius, which is about 750 degrees Fahrenheit. Chemosynthesis is a process where bacteria convert chemical nutrients into organic energy, supporting life in the absence of sunlight. Giganticism is common in deep-sea creatures, such as the giant squid and giant isopod, a phenomenon possibly due to the scarcity of food and low temperatures. The Mariana Trench is the deepest part of the ocean, with its lowest point, the Challenger Deep, reaching depths of nearly 11,000 meters, 36,000 feet, which is deeper than the height of Mount Everest. Bioluminescence is widespread among deep-sea species, used for attracting prey, communication, and evading predators. Many deep-sea species have slow metabolism rates, enabling them to survive on less food. The deep sea is home to some of the oldest known marine species, some of which have changed little over millions of years, such as metazoans, which are 775 million years old, and jellyfish, which have been in the ocean for 500 million years. Deep-sea corals can live for thousands of years, growing very slowly in the cold, dark waters. Brine pools are super salty lakes on the ocean floor, creating a unique and hostile environment where few organisms can survive. Underwater mountains or seamounts are common in the deep sea, formed by volcanic activity. Methane clathrates, also known as methane hydrates, are compounds found in the deep sea where methane is trapped within ice. The Hadal Zone, deeper than 6,000 meters, which is almost 20,000 feet, is named after Hades, the underworld of Greek mythology and comprises the deepest trenches. The abyssal zone, ranging from 4,000 to 6,000 meters, is one of the largest habitats on Earth, but one of the least explored. The abyssal plain, covering vast areas of the ocean floor, is one of the most uniform habitats on Earth, characterized by deep mud and high pressure. The deep sea is the largest repository of carbon on Earth, playing a crucial role in the global carbon cycle and climate regulation. Deep sea mining is a controversial topic due to its potential to harm unknown ecosystems as we search for precious metals and minerals. The cookie-cutter shark, a small but ferocious deep-sea predator, leaves circular bites on its prey. The vampire squid from hell can thrive in the oxygen minimum zone with special adaptations. Sea cucumbers in the deep ocean can process large amounts of sediment, playing a crucial role in the benthic ecosystem. The anglerfish uses a luminous lure to attract prey in the pitch-black waters. Zombie worms feed on the bones of dead whales falling to the ocean floor. Many deep-sea creatures are jelly-like or have soft bodies to withstand the high pressure. The deep-sea dragonfish uses bioluminescence and can produce a nearly invisible red light. Hydrogen sulfide, toxic to most life forms, supports unique ecosystems around cold seeps. The pressure at the bottom of the Mariana Trench is over 1,000 times the atmospheric pressure at sea level. The deep sea is colder than the surface, with temperatures often ranging from 1 to 4 degrees Celsius, about 34 to 39 degrees Fahrenheit. Silence dominates the deep sea, although sound travels faster and farther underwater than in the air. The midnight zone refers to depths beyond 1,000 meters, where sunlight does not penetrate. Trenches and canyons are common geological features formed by tectonic activity. The Pompeii worm is one of the deep sea's most heat-resistant animals, living near hydrothermal vents. The snailfish, discovered at depths over 8,000 meters, is the deepest living fish currently known. Deep-sea exploration is challenging due to extreme conditions, requiring specialized equipment like submersibles and remotely operated vehicles. The yeti crab farms bacteria on its hairy claws to feed itself in the nutrient-poor waters. Marine snow is a continuous shower of organic material falling from upper waters to the deep ocean, serving as a primary food source. The census of marine life was a 10-year project that significantly expanded our knowledge of deep-sea biodiversity. Isolated ecosystems, such as those found around hydrothermal vents, have evolved life forms that are not found anywhere else on Earth. Salinity levels in the deep sea can vary, influencing the distribution of life. The lack of light in the deep sea has led many species to develop enhanced sensory organs for navigation and hunting. Wrecks and artifacts from human history, like the Titanic, lie preserved on the deep sea floor due to the cold and stable conditions. Cold water corals form reefs that can be thousands of years old, providing habitat for deep sea species. Exploration technologies such as sonar mapping and satellite imaging are revealing new features of the deep sea floor. The scarcity of food leads to unique feeding strategies such as marine snow consumption and symbiotic relationships. Deep sea animals often have large, sensitive eyes adapted to detect the faintest light. Conservation efforts are growing in importance as the deep sea faces threats from climate change, pollution, and human exploitation. The deep sea is least disturbed by human activity, yet it's increasingly impacted by deep sea fishing and mining. The lanternfish is among the most common deep sea species, with the ability to produce light through bioluminescence. Marine bristleworms in the deep sea exhibit a variety of forms, with some species thriving near hydrothermal vents. The Lost City hydrothermal field is known for its unique, towering spires of carbonate, unlike the black smokers found in other vent ecosystems. Deep-sea squid can eject ink and often have elongated bodies and large eyes adapted to the dark environment. Some deep-sea fish possess antifreeze proteins in their blood to prevent ice crystals from forming in their cells. Microplastics have been found at the deepest points of the ocean, indicating the widespread impact of human pollution. The sperm whale is one of the deepest diving mammals, reaching depths of over 2,000 meters, 6,500 feet, to hunt squid. Barrel-eye fish have transparent heads and tubular eyes, allowing them to look upwards through their skull to spot prey. The deep-sea octopus has adaptations like long arms and special senses to hunt in the darkness. Phytoplankton, though not a deep-sea organism, significantly influences deep-sea ecosystems by providing a primary food source through marine snow. Undersea earthquakes and volcanic eruptions are common in the deep sea, shaping its landscape and ecosystems. The Dumbo octopus, named for its ear-like fins, is one of the deepest living octopus species. Thermal adaptation allows deep-sea creatures to survive near hydrothermal vents where temperatures can vary drastically. The grenadier fish are among the most abundant deep-sea fish, living in depths up to 6,000 meters, almost 20,000 feet. Deep-sea mushrooms, a type of coral, were only discovered in the 21st century, highlighting the ongoing discovery of new species. The deep sea has its own lakes and rivers, formed by differences in salinity, temperature, and density of the water. Some deep-sea species have lifespans that are much longer than those of terrestrial and shallow water creatures, due in part to their slow metabolic rates. The bone-eating snotflower is a worm that consumes the bone of whale carcasses. The black swallower can ingest prey over twice its length and 10 times its mass, thanks to a highly expandable stomach. Many deep-sea creatures exhibit hermaphroditism, being both male and female, which is an adaptation to the sparse populations. The deep sea supports ecosystems around dead organic matter, such as whale falls, where a dead whale's carcass supports deep sea life for decades. Bathypelagic fish are adapted to the darkness with features like slow metabolisms and enhanced senses other than sight. The abyssal gigantism phenomenon is also seen in arthropods, like the giant deep-sea isopod, which can reach lengths of over 30 centimeters, 12 inches. Some deep-sea animals use counter-illumination, emitting light from their undersides to match the faint sunlight from above and avoid casting shadows. Deep-sea scavengers, such as certain species of crabs and hagfish, feed on the remains of dead animals that fall from shallower waters. Manganese nodules, rich in metals, are found on the abyssal plains and are a target for deep-sea mining, raising environmental concerns. The pressure at extreme depths affects the cell membranes of deep-sea creatures, leading to the evolution of unique biochemical adaptations. Census of deep-sea life initiatives aim to catalogue the species living in these remote habitats, many of which are still unknown to science. Deep-sea sediments can provide valuable clues about Earth's climate history, containing fossil records and chemical signatures. Deep-sea animals often have reduced or absent eyes, relying instead on other senses to navigate and find food in the dark. Chemical signals are crucial for communication among deep-sea species, used for mating, marking territory, and signaling distress. The squat lobster forms dense populations around hydrothermal vents and cold seeps. The tectonic activity at mid-ocean ridges creates new seafloor and hydrothermal vent ecosystems, driving biodiversity in the deep sea. Sea pens, resembling quill pens, are a type of coral that flourishes on the deep ocean floor. Transparent species in the deep sea, such as certain jellyfish and shrimp, use their lack of coloration as camouflage in the dark waters. The deep sea's isolation has led to a high level of endemism, with many species found nowhere else on Earth. Acoustic tagging and tracking are used to study the movements and behaviors of deep-sea creatures, often revealing surprising migratory patterns. The frilled shark, a living fossil, is rarely seen and lives in the depths of the ocean, with a body shape that has remained unchanged for millions of years. Deep-sea fish have special adaptations to deal with high levels of ammonia in their bodies, a result of their unique metabolic processes. The importance of deep-sea ecosystems in global biodiversity and environmental health is increasingly recognized, leading to calls for their protection. Nitrogen-fixing bacteria in the deep sea play a crucial role in the nitrogen cycle, supporting life in nutrient-poor waters. Subduction zones in the deep sea are areas where Earth's tectonic plates converge, often leading to seismic activity and unique geological formations. The gulper eel has a massive mouth and expandable stomach, allowing it to swallow prey much larger than itself. Deep-sea exploration missions often discover new species, with estimates suggesting that millions of unknown species still inhabit these depths. The adaptation to high pressure involves changes at the molecular level, including proteins and membrane structures, to maintain cellular functions. The mirror effect is used by some deep-sea animals, reflecting ambient light with their skin to create a camouflage effect. Conservation efforts for the deep sea are challenging due to its vastness and the difficulty in monitoring human impacts, but they are crucial for protecting this unique environment.